Thanks, Joe. All right. Pop back over. All right, cool. All right, so send these off back to here. So today, I'll wait for people to pop in. Hello, Lily. Kind of doing the same thing we did yesterday, just more on that. I used to have a teacher. Her name was Miss Fraley. Oh, she's retired. She used to be a mom. Walk like this, and a board and chalk. Students, in distress. This is algebra, right? Get to that. I don't know where I was going with that. Tired. 3 a.m. baby. Round 2. Okay, so oh, she would always say moron. We'd have a moron day because we need to do moron the last lesson, which was kind of a stab at us because it meant we were dumb enough that we couldn't get it the first time. Now, when I say that, I don't mean moron as in you are morons. I literally mean M-O-R-E. Retired of my freshman year. She scared me when I had her for study hall. She's wonderful. She still asks. It's funny that I became a math teacher despite all the things I did to her and made her miserable. All right, so Brennan's here. We're going to do more on what we did yesterday. No Grant today. Got Paul, no Parker. Jocelyn Blaze, Afton, Connor, Carly, Joe, where are you? So let's get used to this thing. Hey, here we are. Hey, Joe. So yesterday, just a quick recap. Hi, Carly. We did the first 2 problems on this because people were like, you know what? When are we getting to shapes class? I miss shapes. I was like, okay, fair enough. Here they are. I hope you're happy. We did the first one, and we talked about how that L shape, that little red L, is 7 centimeters, and we were able to take that L and kind of slide it on over, right? I can't really do it. Yeah, it's out of frame. But slide it on over to this side right here. And since those L's are the same, that must also be 7. And then we had 4 little segments here. We had 1, 2, 3, and 4 at the bottom. And since the L is also 4 segments long, we said that must be 7 as well. Basically what we were saying is that you're allowed to take a shape that looks like this, something like that, and you're allowed to rotate it, and it's still going to be the same before and after. I am not good at drawing right now. These are totally the same shape right here. Totally the same. Okay? Hey, Connor. Hey, Afton. We're also allowed to take that shape, and since it's 4 segments long, we're allowed to bend it like that and still have it be the same length. Again, this shouldn't be shocking to anybody. We asked about how do we prove that? How do we know that that works all the time? And we don't. We talked about how there is a theorem in mathematics that says there are things that are true in math that we'll never be able to prove. Things that are 100% true all the time, but we won't be able to prove them. And there's a theorem that says that's true, meaning that we've proven that we know things that are true, but we can't prove it. I don't know, kind of bizarre. Oh, Gödel's incompleteness theorem. And so one of these things we can't prove is called the segment addition postulate, or if you're in my second hour class, the Corinne Postulate, because she came up with it yesterday, actually. Unfortunately, Euclid beat her to it. He's an old Greek guy. The segment addition postulate, which says, look, you can take the pieces of a line, the segments, you can rearrange them in any order you want, and it'll still be the same length. This is super useful, because imagine your boy wants to measure the classroom, right? If I can't stick a bunch of segments end to end and have it be the same length as the classroom, then I can't measure the classroom with this, right? I'd have to have a ruler that is exactly the size of the classroom. When I go to Menards and they say, what size ruler would you like, sir, to measure your project? I have to say, well, it's the size of my classroom. And they say, well, how big is that? And I say, I don't know yet, right? This would be a big problem. So the segment addition postulate is obvious. It is something that if it were not true, we wouldn't really be able to do much. And I used the analogy of talking to my mom the other day, where she was talking about how all politicians lie. I can't decide one way or the other, so I'm just not going to do anything. It's like, that's one way to live. There's no problem with that, right? But for me, as a mathematician, as a person, I would rather take a leap of faith instead of feel like I'm locked in analysis paralysis and I just can't do anything ever. So mathematicians said, look, if this weren't true, we wouldn't really be able to do math. And math is interesting and beautiful and allows us to do lots of cool things. So we'll take the leap of faith to allow us to actually do something cool. Even if it's wrong, right? Fine. But it's more interesting if it were right. And I think a lot of time people miss this when they talk about mathematics. They think of it as a science, right? Only things that are 100% true, or at least they are until they're proven false. No. We know that at some point you have to take a leap of faith. And then after that, you want to build as much as possible, right? You want to take as few leaps of faith as possible, right? You don't want to just build it on a bunch of nonsense. But at some point, you have to have that as a foundation. So Grant is here, Connor is here, Carly is here, Afton is here, Blaze, did I see Blaze? I have not seen Blaze. Jocelyn, donde está? The Grant is not. Wait, no, I saw Grant. So Grant, Connor, Afton, Carly, Joe, gotcha. Still waiting on Jocelyn and Parker potentially. And Blaze. Okay, cool. So segment addition postulate. We're allowed to take the segments and move them around. This is very good because if it weren't true, we wouldn't be able to do this problem. We wouldn't be able to do math. We can take these 4 segments here and wrap them around here to make another L. So that's going to be 7. And then this will also be 7. So a total of 21. Okay? Then we took a look at this guy right here. And we know that this much, again, we're talking 4 segments it looks like, or at least it appears to, right? This doesn't really have tick marks on it. See if I can highlight those. Blaze is here. Awesome. All right, Blaze, I'll get you here. So notice this bottom part doesn't really have tick marks like the top does. But we can tell because it's a rectangle that the top is always directly above the bottom, right? And so if this is 3 segments long up here, then this also has to be 3 segments, right? That's going to be a very useful tool. Don't forget about that. You guys are like, oh, this is boring, easy. And then as soon as I ask you a question that's not this easy, that uses the exact same idea, you're going to lose your freaking minds. Happens every year. So we have 3 segments down here and 1 there for a length of 18, it says. In a normal math class, it's like, okay, well, how long is 1 segment? And then you add them all up. No. Way easier to do this. That L goes here. That's another 18. And then this is 2. And we said yesterday, oops, that's not what I want. We said yesterday that if you have 4 segments, and we know that they have a length of 18 centimeters, to figure out 2 segments, you can do this. Now, this looks awful. This looks like an algebra problem that you probably screwed up before, right? This is not hard. Now, you might be like, okay, I remember you cross-multiply, blah, blah, blah. First of all, we don't cross-multiply in here, and I'll explain why another day. It's a terrible idea. It works like 90% of the time, but the other 10% is the time that you really need it, and it fails you. But regardless, this is not a hard question if you know what it's saying. 4 divided by 2 equals 18 divided by... No, God, no. Division is all about relationships. Division is all about relationships. And you probably were never told that before, right? Division is taking a bunch of stuff and dividing it up, right? I have 4 M&Ms and I have 2 friends. What does that mean? Well, every friend's going to get 2 M&Ms. In other words, you are a very sad person. So, what it really means is it says, look, the relationship, that's what division means, right? The relationship between 4 and 2 is the same as the relationship between 18 and an unknown number. So 4 and 2's relationship is the same as 18 and what? Think about it. 4 and 2 has the same relationship as 18 and what? 9. 9! Right? The relationship is half, or double, depending on which way you're going, right? 4 divided by 2 is 2, right? So it tells you the relationship. See how division tells you their relationship? 21 and 7 have a relationship of triple. Or if you want to go like this, that's just saying the relationship between 21 and 7 is 1/3. 7 is 1/3 of 21. Right? Depends on which way you're going. 21's 3 times bigger than 7. 7 is 1/3 as big as 21. That's all it's saying. That's it. That's all it means. So the relationship is double. 4 is double of 2. 18 is double of 9. That's it. So we know if that this L is 4 pieces, and it's 18, then we know that the 2 pieces must be 9, right? And again, I'm not saying this should blow your mind like, oh, you have to really think about this 12 different ways in order to understand this problem. No, you don't, right? I bet you guys could figure out, 18, that's 18, that means this is 9, add them all up, right?
Adam.
Oh no, my sound isn't on. Right? But eventually, it's going to be a little bit more difficult. Speaking of which, right, relationships are sometimes messy. These are nice relationships. That's like the group that you're like, oh man, they're just meant to be together. 4 and 2, 21 and 7. Oh man, look at that. Just magic. Magic. Okay? The ones that really belong together are like this. What's the relationship between 5 and 5? Well, they are one and the same. Aww. They come together and they make one. That's cute. But then you have those couples where you're like, oh man, what are they doing together? They are not good for you. I have a nephew, or at least I used to have a nephew. Long story. And his mother is very like new age and hippie and cool. And so instead of the kid saying, I don't like that, I don't want that, or no thank you, he has him say this. And I don't think she made him say it. I think he picked it up from his mom. And you offer him like broccoli and he's like, that's not right for me. That's not right for me. And it's like, oh, Elliot. 5 and 5, oh, they're just right for each other. Now, what's the relationship between 5 and 7? Oh, no. That's not right for me. That's you guys. That's a fraction. Ladies and gentlemen, when I write this, you see division, don't you? When I write this, maybe you see division. Maybe. When I write this, maybe you see division, but this one you probably do, right? I didn't change the way I wrote it. I just changed the numbers. If I write 2 plus 2, and I write 3 plus 5, I bet you still see addition both times, don't you? Even though I changed the numbers. But for some reason, in your tiny little brains, okay, smooth brain, right? That's what the joke is. When I change these numbers to 5 and 7, you no longer see division, you see a fraction. And I think it's because you have past trauma from math class. I'm sorry for that. Fractions are not scary. They're actually kind of your friend. They're not really your friend, but they're kind of your friend. When someone asks you what's 4 divided by 2, you just say 2, right? You don't have to think about it. When someone says 21 divided by 7, after you think about it for a second, you probably say 3. 5 divided by 5, 1, right? When someone asks you what's 5 divided by 7, you run for a calculator, don't you? Am I right? Am I right? And there's nothing wrong with that except you're wasting your time. Because what's going to happen when you grab that calculator? Well, you're going to do 5 divided by 7. It's going to give you a decimal, right? It's going to be a little bit more than 1. Or, I'm sorry, a little bit less than 1. 5 out of 7, right? A little bit less than 1. It's going to be some decimal. And it's going to go on and on forever. Maybe you'll get lucky and it'll repeat. It'll be like 0.3 repeating or something. It ain't. Okay? And maybe it eventually stops. I hope so. But most of the time they won't. And so what are you going to have to do if you write down your answer? What do you have to do if you get a really long decimal for your answer and you got to write it down? What do you have to do? Round it, right? They'll tell you round to the 10th, round to the 100th, round to the 1000th, something like that. And what is rounding but estimation, right? So you're telling me you went to your calculator and spent the time to type something in to get an estimate? Dude, I can estimate it right now. It's a little bit less than 1. You want a better estimate? Oh, great, fantastic. I'll grab the calculator if you really need it. But if you need an estimate, you don't need an exact answer. So it's subjective, right? Round to the 10th, round to the 100th. They're just making crap up. You know what's a really exact answer that doesn't require any rounding? It's exact. No rounding, no estimation. And you don't need a calculator? 5 divided by 7 is 5/7. Exactly. No more, no less, no rounding. And you didn't need a calculator to do it. So you're more than welcome to grab a calculator when you see something like this. What's 5 divided by 7? Oh, right, go for it. But like, it's kind of a waste of your time and mine. Because then you rounded to the wrong spot. Or maybe you hit 5 divided by 71 on accident and didn't realize it. Now I'm trying to figure out where'd you get this number from, right? When you see 5 divided by 7, you know what the best answer is? At least what I think. 5/7. It's exact. No work needed. That's it. The relationship between 5 and 7 is 5/7. What does this mean? Well, before we said, look, the relationship between 4 and 2 is 2, right? Double. 4 is twice as big as 2. 5 is 5/7 of 7. Seems kind of redundant, right? 5 is 5 out of 7 of 7. Here's 7 pieces. 1, 2, 3, 4, 5, 6, 7. And they're all the same size. Trust me on that. There's 7, right? How much is 5 out of 7? How much is 5 sevenths, right? Well, 5, here's 5 pieces. How much is that compared to 7? What's the relationship? Well, it's 5 out of 7. That's it. Seems kind of silly. Here's 4. Actually, let's do 2, because 2 is on the bottom here, right? 7 was on the bottom there. I'll try to keep it consistent. There's 2. How much is 4 compared to 2? It's double, right? Twice as many. That's all fractions are. Now, adding them and subtracting them can be kind of difficult if you don't know what you're doing. And we'll talk about that eventually. But that's all these guys are. If you don't like the word fraction, think about ratio. Ratio just means relationship. Okay? And that's all we're talking about. So let's go back to here. I can hit a button for this now, can't I? Awesome. How do you solve a problem like Maria? This is where we left off yesterday. So I'm going to draw this on a piece of paper so it's easier to see. Speaking of which, I'm going to get more paper for you guys and eventually try to get you some binders. In fact, here's what I want to do. If you can, do me a favor, because I'd rather not collect more binders than I need. If you are of the financial persuasion to be able to afford your own binder or steal one, right? I won't ask questions. Steal from the kid that can't afford it. Do so. Get yourself a tiny little binder. It doesn't have to be gigantic. It can be tiny. I stole this from my dad. This guy right here. Fellowship of Christian Athletes. Stole it right off his desk. I had to do it for the irony. And I'm going to fill it up with graph paper for you. It's going to be a little math journal or whatever. I don't want to call them notebooks. When you think notebook, you think take notes in class, and then we get this, and you don't do any learning. Right? Right? That's you. Down a little bit. So I want you to write and play with your math, kind of like I showed you the other day, right? How do I come up with these lessons? Well, I'm playing with numbers, figuring out different ways to think of them. I want you doing that as well. But anyway, I'm going to write this down. Here's our drawing. We had all 3 flavors of shape on the board. We had rectangle, square, and this guy. I'm rather partial to this one. So this length is 13 centimeters, they're saying. Okay. Cool. What's the perimeter? In other words, the perimeter, the length around the object, right? How do you solve a problem like Maria? People online, you're more than welcome to participate. You were here yesterday. Lily, give him a break, though. Lily is like my student teacher. She's in college right now. She's a former student of mine. She's going to virtual student teaching. How would you solve a problem like this? Where are your gods now? Before you're like, oh yeah, yeah, okay. All right, I see it. Okay, Mr. Back. Tough one, huh? Now, normally, we don't assume anything because you know what it does to us, right? And we have to remember this in geometry all the time.
Take it easy, it's just a drawing.
Right? You can't assume. But I will tell you right now that these are 90-degree angles, right? Grandpa SquarePants, rock bottom, never chase after a bus, especially one that's going up at a 90-degree angle. In other words, what this means for you is that this line right here is directly above this line, okay? And this line right here is directly next to this line, okay? It's not at a slant. This is not necessarily longer than this. Yesterday we had a student say, hey, what if we extended this down? I don't know. This line right here would be directly across from that. This would be directly across from that. And if you can't figure out the actual question of what the original shape is, maybe you can tell me some other stuff that might be helpful. What do you see? What do you notice? No, don't help them figure it out. I want them to think. It's not something we do a lot in school. Yeah. What are your thoughts? For future reference, if I call on you, unlike, you know, if you haven't raised your hand, unlike in other classes where it's like, Paul, what's the answer? And then you're like, 7, and we're like, no. Or close. Is it 8? No, closer, right? And what are we even doing, right? And here when I call on you, I'm not asking for an answer. I'm asking, do you have any thoughts on it? And if you have any thoughts, then make sure you're thinking, right? So Paul, do you have anything you're thinking about right now? Chase? Any idea of where to start? Anything that you see that might be helpful or might, you know, something we can put on our diagram to later use? Hey, Sandra, any idea? Oh, the extension thing? Oh, really? Awesome. That's cool. How about you? No? Could be. Why do you think subtraction? Sure, sure. So think algebra for a second. I know you guys hate it, but if you add something to both sides, right, in order to not have it change the problem, right, you have to subtract it away later, right? There's a little balancing going on. So we added this on. So if we just calculated this, that's too much, right? Or at least it's not the same shape, right? It probably will give us a different answer. So we'd have to subtract it later. That's a good idea. What do you have to say, Chase? Is it drawn to scale? So you count rectangles or count boxes? Is that what you're doing on graph paper?
That's 13.
Oh, so you're saying that this and this, it's a halfway point? How do you know that for sure?
I don't know.
Okay, so he's wondering, can we assume that this is 6.5 and 6.5? Can you imagine a shape that was a little longer this way and shorter this way and still would, like, can you imagine stretching this side out and shrinking this side a little bit? Maybe it's like, I don't know, 10 and 3. Just because this and this looks to be the same doesn't mean it is. That's what he's asking by, is it to scale, right? Again, sorry, this one.
Take it easy, it's just a drawing.
Both have SpongeBob and Patrick standing next to themselves in the GIF. I don't have them labeled with words. Hard to fit, take it easy, drawing in that tiny little box. You know, right now it's kind of hard to talk about it. So a lot of times in geometry, what they'll do is they'll label the points where it bends, right? So let's do A, B like they had in the drawing. It's going to look kind of gross. Usually I try to do alphabetical order. Like that. So if you want to talk about a particular segment, what you can do is you can say, look, I want to talk about segment AC. You can say segment AC, or you can write something like that, okay? It has a little line above it. That's how you know you're talking about a segment. Now again, to be clear, because Chase was asking if it's drawn to scale, the angles are drawn to scale. This right here sits directly above this. And this right here sits directly above that. Right? Go ahead. Make a conjecture.
Yeah.
So you're saying this, 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 and this are all the same? How do you know? They look like they should be. Because they're all 90 degrees? What do I think about that? Can you imagine a shape? Because again, they don't specify the length of these, otherwise we just add them up, right? So imagine a shape like this. This shape is technically the same as that one. If we don't know the lengths, you see what I'm saying? Now, this is where geometry gets kind of weird, right? We're working in imagination land. Your version of an L shape, if I just said, imagine an L shape in your head, you could have come up with something like this or like that, right? And all I'm saying is that the top part of the L and the right side of the L are going to be 13. This is where things get weird, right? You can't pull out your ruler because in imagination land, your ruler is imaginary as well, right? We don't know how long these are. All we can do is compare it to what we already have. So if I were to give you a line segment and I said, look, this line segment right here, which lines up perfectly with that, that's 5. Well, then guess what? You know this is 5 as well, right? It kind of serves as a ruler. Now, does that mean you know this is 5? No, because it's not lined up next to it. That's where it gets weird. That's why we're spending time on these kind of easy problems that are kind of silly, because a lot of geometry is being able to think in imagination land, and things that are easy in real life are a little bit harder in imagination. There's lots of ways to do this. They might not be thinking the way you are, because I don't think I'm thinking the way you are, Lily. How do we solve the other problems? Take a look at them. I got this somewhere, so they're probably connected in some way. Yeah, their drawing doesn't look exactly like mine. That bottom part looks a little bit bigger. The beauty is with geometry is you don't have to be exact in your drawings. What if we make an easier problem? One of the strategies I want you to develop is that if you can't solve this problem, find a problem that's similar, right? Because that might help you solve the more complex problem. This happens all the time in science and mathematics. They solve a way easier problem instead of a problem that they've been working on for hundreds of years, and that problem leads to a breakthrough in the harder one. What if I told you this much was 13, just from here to here? What would that tell you about this? It has to be 13, right? Because it's straight across. It's kind of like a ruler, right? This would serve as a ruler, and because it's lined up with this is 13 as well, right? Does that tell us how much this is and how much this is? No. It could be 10 and 3. It could be 6.5 and 6.5, right? We don't know, but together they'd be 13. Segment addition postulate. The pieces of this, right, add up to 13. So if this was 13, bam, we're good to go. Same thing here. If this was the part that was 13, then this would be 13, yeah? What will this piece right here? Let's go F to G. FG will be the same length as what other piece? Guaranteed, has to be. Say again? ED, right? No jokes. FG and ED would have to be the same length, right? What would AF have to be the same as? Well, if you look, right, if we extended this out, right, let's call that, instead of using H, because H, if you turn on that side, looks like an I, right? I skip and go straight to J. You're going to get used to that. This would have to be the same length as that, right? Okay, so this is the same as that, is the same as this. This is the same as mystery piece that we haven't put in yet, the same as that. Right? It all slides over. And this slides down to here. So this bit right here is the same as this bit here, yeah? That bit is the same as this bit. This bit is the same as that bit. This bit here is the same as that bit. This bit here is the same as that bit. No, we're not there yet, Macy. You're gonna be fine. Don't worry about it. You're thinking too hard. Do you like how I change things up, though? You're like, no. So this bit right here altogether should be the same as this. Right? Because this much goes with that. 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 I don't know what all the individual pieces add up to. Or I'm sorry, all the individual pieces are, right? But I know that this, and this should add up to the same as this, and this. So how long is the blue only segment, or the blue only L? It has to be 13 as well, doesn't it? So now we know something. This much is 13, this as much as 13 as well. But we want the original image. How do we account for that? See, the problem with subtraction is we have to be able to remove stuff, and we don't know how much things are to remove, right? That's the issue. I don't know how much this is. If I could remove it, right? What I need to find is something that is equivalent to that. Even though I don't know what they measured, right? I don't know if this is 5 and this is 5, but I know that they're equal, right? So for instance, how long is this pen? No idea, right? You have no idea how long this is. But you know that it's the same length as this one. The potato. You don't need to know how long they are. You just know they're the same. I don't know how long this is. But I know it's the same as what? I'll give you time. That's okay. Don't answer my question. Answer your own. Oh, I thought you were going to say, I'm not sure what you're asking, but here's what I have to say. Oh, you just don't know what you're asking. Okay. So we know the length all the way around here, but we want to get this part, right? So what are these parts the same as that we can figure out kind of? So this part FE is the same as, or you said AF. This is the same as CJ. Very good. So we line those up. That's fine. What about these guys? What about FE and ED? Okay, give me which ones are similar. FE and DB. How do you know that they're the same? Between A and C. Okay, yeah, like a K because we already have G. This is a K. Okay. Yeah, you can add points anytime you want. So this is a K. And then like this to make it easier. So what's going on here? Yep, these two have to be the same. That's good. And we've kind of already accounted for that, right? This is part of the 13 here. It's these guys that we need to either get rid of or replace with something that we do need, right? Yeah. Okay, words are hard. GD and FE are the same. I think this is using Macy's method. So this guy right here, we need to know about this, right? FE. And Chase is saying it's the same as GD. How do we know that? Anyone but Chase. It might not be half, though. That's the problem, right? Like, imagine it's this, right? That's not necessarily, well, I guess that kind of does look like half, but, right? That's the thing we got to avoid. It looks like half. We only know relationships between pieces. We don't know what the relationship is. We either know it's the same or it's not the same, right? This is going to be the same as this because they're right over the top of each other. I want you guys to work on this. Write about it in your portfolio, please. Can you talk about what we have done? The L thing, right? However far we've got, however much you understand, I want you to try that. If you can solve the whole thing, or if you think you can solve the whole thing, go for it. But if you can't, that's fine. That's fine. Hey, Campbell. Take it easy, guys. And, oh yeah, today's Tuesday, not Friday. Later. Let's say have a good weekend. Good job today. You feeling okay? You doing all right?
Just tired and that's all 4:30.
Right. So other than that, but life is pretty good. Okay, bye. Hey, everybody. No Jocelyn and Parker last hour. I'm gonna throw this up on the screen so you guys can take a look at it. I'm gonna use the restroom real quick. I've got my, look at this. I've got a camera for the board now. It's that crappy one that we got for free from the school. So I'm probably gonna replace it. As you can see, it's a little glitchy. but I can hit a button whenever I want and just pop over. I'm gonna leave that here for now. This is what we did yesterday, for those of you that were here for it. Let me spray stuff down. Yeah. Oh, Sarah. Hey, y'all played that new game, Among Us? I love it. Game Club's going to be doing a giant Among Us kind of party. It's going to be great. You played it, right, Jace? Have you played Among Us? I know Lindsay has. Are you trying to, wait, is it Lindsay Altenhoff or is it Lindsay Schrader? It might be Lindsay Schrader. I know you're friends with Lindsay Altenhoff. Yeah, that's fun. And I'm real good. You know what we're talking about? Among Us. It's kind of like a like werewolf, actually, the hidden role type of thing. There's always a traitor, and they go around the ship and they murder somebody, and it's like, who did it?
You feel the type of person.
Oh, I'm good. What I do is I wait till everybody's like right next to each other, and I do a murder, and they don't know who it is, right? Because you're also close by. Thought you were safe in numbers. I'm so good. I'm so good. I murdered like 8 people out of the 10 within like a minute. It was amazing being caught on that game. And then the next game, I got it again. Like I was lucky enough to be the traitor, and I started murdering really quick. And they're like, okay, it's that guy. There's no one else that can pull off this many. My reputation precedes. All right, I'll be back. I'm in charge. And actually, you know what? Not him. Not him. Okay. Bartos? Y'all met Mr. Bartos? Man's a living legend. Haley's already pulling out the calculator. She's like, okay, time to do math. 5 times 5, 25. 6 times 6, 36. 7 times 7, 49. Yep, still works. All right. Hello. All right, so let's take Tendi. This is what we're working on today. Same thing as we did yesterday. We're going to get to problem 3 in a second. I'm going to catch you up on what we did for problem 1 and problem 2. No judge. Those of you that are here today, were you here yesterday online? And if you weren't, that's okay. I just want to know, yeah, exactly, right? Not because I want to police you or anything. I just want to know, like, how much catching up should I expect to do on, every other day? Can I roll like you were here? Or do I need to go, hey? No, wonderful. Remember, this is something we have to write about in your portfolio. Having 2 days to learn about it and understand what's going on is a lot better than 1. Your call. And that's not meant to be a dig. It's just, I'm trying to give you a heads up. Campbell, Shion, Mika, Katie, Annie, Olivia, Blake, Jaden, Theron, and Marissa. I'll see. Marissa, I saw your video that you made with Natalie. I liked it. I went on YouTube and I liked it. No, McCartney. I see Jaden. Any Lauralee online? I don't see Lauralee. I think I got everybody else though, right? I got Blake? Yeah, we got Blake. Awesome. Okay, cool. Rad. So, yeah, like I said, we got a new camera. And by new camera, I mean we got an old camera that I got for free from the school. As you can see, it's pretty glitchy. I'll be replacing it with one that is a wider lens. Actually, it was the first webcam I ever got back in like 2013. And I got a wide lens because I wanted to teach with it, right? And so that would actually be perfect to go right there. I finally got the USB extension cable to get it over here. And I've got this finally set up. I originally got this not to be a soundboard, but we'll switch between cameras really quick during Corona. So I can just pop back and forth between all these. Loving it. Loving it. I know you're excited, Sarah. Just try to contain it, okay? All right. Once Sarah's ready, we will begin class. People online think you're nuts. They don't know. I could turn off the camera. I could just, like, have the button right now, but I could turn off all of them. I just, like, Sarah, leave me alone! Sarah, Sarah, Sarah! They'd believe me. All the cops be real bad. Okay. Welcome to class. No smiling in math class, Haley. Good. You just look like that? How long have you looked like that? Whole life? So, yesterday, what we talked about was shapes. We had all three flavors. We had square, rectangle, and that guy. My favorite is the third one. I'm rather partial. And we said something like this. We said, look, if you check out... I need a better pointer. That's the next thing I gotta do. So if you check out this guy, you can't even see that, can you? You can barely see it. You see it? You see it?
Yes, sir.
Yeah, you see the circle popping up? I need to make that better, like yellow or something. Do other teachers have that, where they have like a yellow pointer or something?
They don't.
Okay. See it now? Okay, I'll get better on that. So anyway, we said this L thing on the first one. That L thing right there is the same as this L here. And we know that because, look, it's 4 segments long. Right? It's 4 different segments long. And this is 4 segments as well, and the exact same shape. We said yesterday by Corinne's postulate. And again, you guys don't have class with Corinne. Oh, what am I doing? I've got buttons, I've got buttons, I've got buttons. There's our shape. Ignore that. He was born with a tail, they had to take it off. Like Haley. So this L right here, we know is the same as this L here. Has to be. Why? Because if you look, it slides over, and this slides down, and they're the same length, right? That's not too far-fetched. I think I've convinced you of that. You're going to not remember that later. It'll happen. Calling it right now. The problem we have is that we have this, right? And they give you little tick marks. They divide up the line segments into smaller segments. Oh, hi, Corinne. We're talking about your postulate. And we said that this is 4 long, so this L right here, being 4 pieces, is the same as, that's what equal sign means, this L, because it's 4 pieces. You dig? Right? We said that's acceptable, that you're allowed to take the pieces apart and rearrange them, and they still be the same length. And this is very useful because imagine if Mr. Mack wanted to measure his classroom. If I couldn't take the pieces apart and put them back together and they'd be the same length, I couldn't lay this end to end and measure the room. I would have to get a ruler that is exactly the size of my classroom, which would be a problem, right? I go to the Home Depot and I'm like, hey, I wouldn't go to Home Depot, I'd go to Lowe's. Go to Lowe's, I wouldn't go to Lowe's, I go to Ace Hardware, okay? Do you know that they're individually owned small businesses? They just have the Ace Hardware brand. Lovely people. You go to the counter, there's someone who's like 80 years old, and you're like, I need this like really bizarre screw, and I show them it, and they're like, oh yeah, I've seen one of these back in '88. We've got them in the back, right? You go to Lowe's or Home Depot, and they're just like, sir, this is just my day job. I don't know what's going on, and God bless them, right? God bless them. But Ace is the helpful place. Anyway, I go to Ace, and I'm like, okay, look, I want to measure my classroom. I need a ruler the size of my classroom. Because in this imaginary world, I'm not allowed to put these end to end, right? And they go, okay, great. We have lots of rulers. How big is your classroom? I say, well, I don't know. I don't know that yet. I can't tell you. Well, then we can't get you a ruler that's the size of your classroom. Do you see the problem here, right? It's a chicken or egg situation. Really, really quite the conundrum. So we're saying, look, we can't prove that you're able to take the piece apart and put them back together and have it be the same. We can't prove that. We spent hundreds and hundreds of years trying to. But if we couldn't do that, there's not much we can do in math. Like my mom when I was talking about her the other day, right? You guys were here for the show. You were here yesterday. You heard me talking about my mom. She's like, candidate A says this, candidate B says this. I can't tell them apart. They're both liars, so I just don't do anything. I can't tell, right? Throw my hands up. Nothing you can do. I'll just stay inside. And that's fine. You can live your life that way. There's nothing wrong with that. My mother does. I, on the other hand, like most mathematicians, say, look, it's far more interesting a life to live if we are able to do things. That some things are true even though we can't prove them for sure, and we act on them anyway. We take a leap of faith. And it turns out mathematics is built on leaps of faith. We call them postulates. A postulate is something that isn't proven and probably can't be. But it has to be true, because if it wasn't, we wouldn't be able to do anything without it. All of math comes down to, at the beginning, a leap of faith. We call this the segment addition postulate. Some of you guys call it Corinne's postulate, because she came up with that yesterday. I like segment addition only because it says SAP, and that's easy to remember. Segment addition postulate, again, not something we prove, but it says you can take up the individual pieces and then add them back together however you want. That's where the addition comes in, right? Any shape, and they'll still be the same length. So we took the red one, rearranged it, and made this totally valid. What was weird is that yesterday, we also found out that this must be the same as well. They said this red piece is 7 centimeters. Which means this blue piece is 7 centimeters. Okay, I can see it. But this one's kind of a different shape. It's an L, but it's not like this L, right? Like this L. Equal length on both, right? 2 segments each. And again, segment addition postulate takes care of it. Not only is that equivalent to that, but this is also equivalent as well, because at the end of the day, they're all the same number of segments. The shape doesn't matter. And you're like, okay, boring, duh. Then I'm going to get to problem number 3, and you're going to lose your minds. How do we feel about this idea? You say that now. Number 2! You have this L, right? And you notice that you can flip it. No, you don't need math class. You can flip it like this, right? So if this L is 18, this L is 18, what about the side over here? That's something different. Not 4 pieces, is it? We're going to talk about relationships. I need like a set the mood button. The Marvin Gaye. You guys all seen Rio, movie with the birds, right? Who's the one person that they listen to and like, ooh, yeah. It's the one guy, he really likes him. No, it's not the bird, it's like the music they turn on. Who is it? I worked with a teacher that loved this. Lionel Richie. Right? Ooh, Lionel Richie. And they're like, ooh, yeah, feeling it? I need some Lionel Richie to play. We're going to talk about relationships, okay? We're going to get the T, as the children say. What's in the box? What's in the box? You guys know that movie? It's called Seven. If you're going to watch a Halloween movie, it's a great one to watch. And they give you tick marks here, here, and here, but they don't give you any tick marks there. And they say that this is 18 centimeters. Yesterday we said, more or less, again, catching you guys up. People online, sorry. We said that, look, obviously this is 18 by segment addition postulate, right? What about this? We're going to talk about relationships. 9! How'd you come up with 9? Divide by 2, right? Boring. And you're correct, it is 9. What you're asking is this, okay? You're saying, look, I know that 4 segments should relate to 18 centimeters, right? 4 segments equals 18 centimeters. You cool with that? I could write segments here, but I'm not going to. We cool with that? Well, we're talking about relationships. 4 segments relates to 2 segments. They have a relationship, right? That relationship is double or half, depending on which way you look at it. And what we're asking is, what's this? Now, you're like, okay, 4 divided by 2 equals 18 centimeters divided by x. No, God, no, please don't read it that way. Think about what it means. Division is relationship. And you didn't know this because no one ever told you, right? They tell division is you have 4 M&Ms and you have 2 friends. What does that mean? It means you're a very sad person. You only have 2 friends and you only have 4 M&Ms, right? But in math class it means, oh, well, everybody gets 2 M&Ms. That's not what division is. Division is better represented by relationships. 4 and 2, what's the relationship? Double, right? Or half, depending which way you're going, right? When we see division, I want you to think relationship. The relationship between 4 and 2 is the same as the relationship between 18 and what? I'm going to say that again. The relationship between 4 and 2 is the same as the relationship between 18 and what? 18 and what? This is where you come in. 90! You don't have to cross multiply or any of that garbage. You don't have to. You can just think about it. Right? 4 and 2's relationship is double. How do I know that? Because 4 divided by 2 is 2. See how it tells you the relationship? 18 divided by 9, is that also 2? Oh, look, they do have the same relationship. We win. Now, some relationships are just meant to be, right? 4 and 2, double. Great. That's beautiful. 5 and 5, what's their relationship? Well, they are one and the same. Aww. That's like that one couple you're like, when are you two getting together? I mean, come on. Right? You're finishing each other's sandwiches. That worked so well, didn't it? Both can be deceiving. Anyway, 5 divided by 5 is asking, what's the relationship between 5 and 5? They're one and the same. But then you have weird relationships. You know, the couples where you're like, oh my god, why is he dating her? Like, honey, you could do better. 5 and 7. Ugh. What's the relationship between 5 and 7? I laughed. That's all you got, right? Well, it turns out the same rule applies. What's 5 divided by 7? Haley, you have a calculator. What's 5 divided by 7? Now, for the record, all I did was ask her, what's 5 divided by 7? I said she had a calculator. Just facts. Yes?
0.71428.
7 for what? 71428. 571. And it ends on that, or are you just out of room on your calculator? Okay. So, forget the calculator. Why? Because you're going to have to round that eventually, or assume that it stops there magically. And maybe it does, right? But most numbers, it turns out, when you write the relationships, come out nasty looking. Sometimes you get lucky and it's like 0.3 repeating. Yay, we can write that. But this you're going to have to round or assume it's done, right? Which means you are what? Estimating, correct? So you're telling me you got out your calculator. You typed it in. Hopefully typed it in correctly. You hit enter to get an estimation. Girl, I can estimate right now. This is not your fault. This is what they've taught you to do. I can estimate right now. 5 over 7. 5 out of 7. What's that about? Well, it's not bigger than what? A little bit less than 1. Between 0 and 1. A little bit more than half, right? A little bit more than 0.5. I don't know. I mean, you're estimating anyway, right? By having to round. Why can't I just estimate by saying about 0.5? And you're like, but I need an exact answer. Well, here's the thing. That's not an exact answer. It's just as rounded as mine. I just chose to round to, 0.5 instead of, 0.71 or something. It's all arbitrary. All made up. You want an exact answer? What's 5 divided by 7? What is the relationship between 5 and 7? It's 5/7. Fractions are actually your friend. They are the easy answer to hard division problems. Now, 4 divided by 2 you wouldn't say is 4 over 2 because there's a nicer answer, right? We call it simpler, simplified, right? It's 2. But this one isn't simplified. We just leave it like that. It's 5 out of 7. Now, why does this make sense? Well, look, before we had 2 pieces, right? And we want to know the relationship between 4 and 2. Well, here's 2, here's 4. Clearly, 4 is double, right? It's 2. What about 5 and 7? Seven pieces need 8 dots. 1, 2, 3, 4, 5, 6, 7. Yeah. Here's 5. 1, 2, 3, 4, 5. Looks like less than 1. Right? Or if you want to be exact, isn't 5's relationship with 7 is that 5 is 5/7 of 7? Isn't 4 double of 2? Isn't 5 1 of 5? Isn't 5 5/7 of 7? See, that's 5/7. 5 out of 7. That's it, man. That's all fractions is. That's it. Now, adding and subtracting can be kind of weird, right? And we'll talk about that eventually. But in general, fractions are your friend. They tell you the relationship between stuff. If someone asked you last year, and they're like, Haley, what's 9 divided by 7? You'd be like, or you get a calculator or something, right? You would look like a genius if you said 9/7. Right? You wait a little bit, you're like thinking about it. People forget the original question. They don't hear that they just said 9 divided by 7, right? They don't see the connection. Is it 9/7? Oh my God, she's a genius. What's 99 divided by 12? 99 over 12. Oh my god, she's exact! That's it. I don't know why we make it hard and make you guys type it in. Imagine you'd go to type it in and you type 5 over 71 on accident. You hit the 1 on the way to equal sign. Now I gotta figure out, why did you get this weird decimal? I have no idea. Anyway. This guy. We know it's a relationship of 2 to 4, right? 2 pieces versus 4 pieces will be the same as 18 to what? 18 to 9s. How would you add those up? Sure, you'd add them all up, but what's an easy way to add them in your head? How would you do it? What's your strategy? How would you do 9 plus 18 plus 18? 18s? You know 18 plus 18? What's that? Okay, you're confident in that? I always have to think. It's 36. I'll do 10 and 10 and get 20, and 8 and 8 is 16, that's 36. And then the 9, right? I can do that. That's just 36 plus 10 minus 1, 45. Another way I like to do it is I say, that's 10 plus 20 plus 20. So that's going to be 50, but I added on 5, so subtract 5 to get 45, right? Make it the same. Let's get to the real deal. The real deal. Number 3. I'm going to draw it. Now, looks can be deceiving. My drawing's not going to look just like that, okay? Did they tell you how long these pieces are? No, they do not. It looks like that one piece below A is really small and the one next to B on the bottom is longer, but do we know that for sure? No, this is imagination land, okay? Just because it looks smaller doesn't mean it is. What I like to say a lot of the time is this. Write that down, write that down! Sorry, not this one. It looked the same, it's a similar button.
Take it easy, it's just a drawing.
It's just a drawing. We don't know if it's exact. We just know that the shape holds up, okay? So here's what I drew. And here's the part that they told us. They told us this much is going to be 13. How do we find the perimeter of the shape? How do you solve a problem like Maria? You're trying to remember what the thing it was that I told you you'd forget, right? Yeah, you are. Don't worry about that. Think. We're going to spend time thinking. Same from A to B on both sides. Okay, so Katie, they had their drawing labeled like this. Let's start labeling it. Normally I do alphabetical order, but they had A and B here. Labeling it's going to make it easier to talk about, right? Instead of saying, hey, that segment below A that's right there, right, we can give it a name. That segment we would call segment EF with a line over the top. Cool with that? Right, that's how we denote that so we can talk about it in our portfolios and stuff. So Katie says A to B is the same on both sides. So you're saying from here to here is the same as here to here? How do you know that? Anybody else in the meantime, you're more than welcome to chime in. Go ahead, where's some up? So you're saying, let's get this, right? And then we can subtract what we added on. Something like that, yeah, sure. How are we going to subtract something we don't know the length of? Remember, how do rulers work? We stick them right underneath the object, and if they line up together, then we know they're the same length, right? For instance, you don't know how long this pen is, right? But you know that they're the same length because when I put them right next to each other, they match, right? Jace.
Where that A and B the same length.
Okay, so when you say AB, I don't know whether you mean ACB or AFEDB.
ACB.
ACB, so the red part, ACB is the same as ACB again. Oh, so AFEDB, or let's put a G here. Are you saying? I love that. He didn't have to say AFGDB because AGB gets the job done. You guys see that? So he's saying this is the same as AGB. How do you know that? I'm not saying it is. I'm asking how. Ooh, we can flip it. It looks like it. Now before we knew it worked because we had 3 segments here and 3 segments here. They're right over the top of each other. And 1 segment there and 1 segment there. Here we don't have any lines like that. But we do have segments. I want you to think about that. Katie, what are you saying? If you take the weird piece from F to D, I'm assuming you mean this one, not this one, and take it out and flip it upside down, it fits. Oh! So Katie is saying FGD, the segment, well, it's actually 2 segments, so we're not going to put a line over it. I think really what we should do is if we want to be exact, right? Because FGD isn't a segment, it's 2 segments. We could do like FG plus, it turns out in geometry, when you're talking about how long it is, like the length, the value, you don't put the line over the top. If you're talking about the figure, you put the line. So FG plus GD should equal, according to you, FE plus ED. And she says because you can flip it over there. Okay, that's what she says. Again, none of the stuff I'm writing down do I guarantee to be true. The first rule in here is trust no one. Case, what do you have to say? And then Haley? That's what Katie's saying. Now, how do we know that they're connected? Right? Looks can be deceiving. It looks like it should just flip into that. How do we know? Think about it. Haley, is that what you were going to say? Okay, what are you going to say? Across? Okay. Let's call that, next letter is H. H looks like I, depending on how you rotate it, right? So I skipped to J. So what are you saying? Are you thinking this is 13?
Yeah.
It's all the way through here. Yeah, it's okay. If it were, though, what would you do? That's fine. Again, asking a similar question might give us ideas about the more complex one. So if this was 13, what would you do? What was your thought? So this would be half and half. Now, question, does anybody have a counterpoint to that? Does that mean this has to be 6.5? If this were 13, right? Just this much. Does that mean that's 6.5 and 6.5? Daryl looks skeptical. Are you? How do we know it's half and half? We know it adds up to 13, right? Has to. Because the pieces add up to the whole. That's segment addition postulate. But maybe it's 3 and 10. You see what I'm saying? Unless you know it's half, you don't. Does that make sense? We're going to have to get used to that. That's a good thought, though. Thanks for bringing that up. Jace, go ahead. So you like this? Ooh. So you're saying all those are the same. That's a big assumption. That's assuming this is half again. Is that what you're saying? Right? We could do... What are you saying? What are you saying? Assuming these are all equal, we could divide by 4, right? Do you see what I'm saying? Right? Maybe this is 3 and 10 and not 3.25, 3.25, 3.25, 3.25, right? Or maybe this is 10 and this side is 3. You see what I'm saying? Right? We have to be careful with that. This is stretchy imagination land. All we know is that we have an L shape. Maybe this is 10 and this part's 3, right? We don't know. What we have to do is we have to match stuff up that are going to serve as rulers. And again, we don't know how long the ruler is. But because it matches up and lines up next to it, like these 2 pens line up, right? Then we know that they're the same length. What do you see that lines up in this diagram? This is good. This is good. Katie, you're onto something. If you can show me why this has to be the same as that, then we win, right? The question is, how do we know that? The only problem is that maybe it isn't, right? So that might be a path we go down that's not valid. But if you can, you win, right? That's the key. Even if you get it wrong, you're seeing a path towards victory. And that's important. Seeing it is half the battle. We need to figure out, just for the record, what this is and what this is, right? What do those things line up with that we can use as rulers? Rulers. before we go, because I don't know what time it is, I want you to write about this in your portfolio. Okay, the first two problems and the third, this guy. I want you to explain them. Hopefully the first two you feel pretty comfortable in explaining, right? Segment addition postulate. If you take the pieces apart and rearrange them, they're still going to be the same. You can add them up in any order, right? Just like adding numbers. The third one, I'm not expecting you to get the answer, but I'd like you to have a solution that you came up with. Whether it's the right answer or not, we'll find out, right? I'll challenge your reasoning. But keep going. Y'all were like, this is boring. First two problems, easy. Why are you talking about fractions? It's half. It's so easy. Move on. Well, we knew it was half before, because this was 2 and that was 4. Right? We don't know that this is half. All we know is that together, all those add up to 13. It could be 1, 1, and 12, or I'm sorry, 11. Who knows? Right? Don't you just wish we could measure it? Measuring doesn't teach. Oh, now I know it's 6.5 for each. All right. I learned today. Next problem, I'll have to measure it all over again. Could be different. We're learning something that's going to work for every problem. When I used to teach music, they'd have like Halloween concerts and stuff, and you have to get them ready. And of course, you only see these kids like once a week, right? And so how do you teach them a song? Well, you don't have time to teach them how to read music and do all this stuff, right? That's really learning. What you have to do is you have to say, repeat after me, right? Jingle bells, and they repeat back. And eventually they memorize it from doing it so much. And then after Christmas, it's time for a spring concert. And everything they learned in Christmas is no good because they're not going to sing those songs, right? If I taught them how to read music, though, can you imagine how the stuff they learned for Christmas might help them later on? That's learning. But I didn't have time for that. And I was demanded I had to have those kids sing. So I did what I had to do. I don't want to do that with math. I want to teach you stuff that you can use over and over and over again, not just it worked for the one problem. That's learning. How do you solve a problem like Maria? Maria is the green part, right? How do we know that this blue part, all the way over, I'm going to extend this out, is the same as the red part? I don't think we've said that yet, officially. How do we know blue and red are the same? Boo! You know what I have to say?
Take it easy, it's just a drawing.
Haley. Is it? It has 4 sides. I'm comfortable saying it's a rectangle. Square means all the sides are equal. Do I know that this is the same as that? No, I don't, right? It could be like this is 3 and that's 10. But if that's 10, then this has to be 10, right? See how they're across from each other? They kind of work as a ruler, so we know that they're the same because they're right next to each other, right? So we know that this, whatever it is the same as that, right? And we know this is the same as that. So if this part goes to this part, and this part goes to that part, right? AC plus CB has to be the same as GB plus AG, which is the whole shape. Do you see what I'm saying there? I know that's the same as that, and I know this is the same as that. So altogether they're the same, right? I'm going to say that again. This part plus this part makes up the red, right? And you see how this part matches with this part in the blue, and this part matches with that part in the blue? All of the red matches with all the blue. So it's the same. Has to. What do the greens match up with? That's going to be the key. Yeah, Jace. Ooh, you're saying this green part matches with KEJ? How do you know that? Let's break it up. What does FE match with on KEJ? What does FE go with? KE? How do you know that? Are they lined up right next to each other? Like this or this? They're not. You have to rotate it, and you have to hope it's the same, right? It's not directly above it, like these two are. You see the difference there? So this could be longer than this one. We don't know. You think about that and that? If I draw two lines next to each other, you know they're the same length? No. They have to be over top of each other and perfectly match, right? You know what I'm saying? So these two we know perfectly match because they're right next to each other across. Same thing here. Haley, good thought, Jace. FE and AK match up. So this goes with that. And then this, I'm going to use marks like that. In geometry, we do that a lot. One mark goes with that, means they're the same. And then this goes with what? ED goes with JB. Agree or disagree? Say it. This could be longer than this one? Why? We don't know their exact length. Jace, do I know the exact length of these pens? But do I know they're the same length? How? How do you know that? If they line up, then they have to be the same. Jace, what do you think about Haley's logic? So you agree with her now? Why did you change your mind? So they line up. Okay, I'll accept that. Anyone want to disagree with Haley and Jace? Or are you agreeing with them? Sarah? Problem's not solved yet, but we've got some insight. Again, trust no one. I'm not guaranteeing that the blue is the same as the red, and I'm not guaranteeing the pink is the same as the green. Oh, Katie's got some. FE and DB added together is the same as A to C. FE and DB is the same as A to C. And DE, you guys can go. DE and AF are the same as this. So you're saying that this piece right here matches up with this, right? So that goes with that red. This goes with this red. This goes with this red. And this right here goes with this red. So if you look, this side has a 4, a 1, a 3, and a 2. And this has a 4, 1, 3, and a 2, doesn't it? So they have to be the same by segment addition postulate. Katie, that's good logic. Right about this. Bye. Didn't even need the side piece, the blue. Hello. Go sports. Is this a real sports team or a virtual or a fake? Like, awesome. Tell me about it. It's what?
It's called IQ.
IQ?
Yeah, the anime that I was talking about.
What does IQ stand for?
IQ.
IQ. Okay, gotcha. I was thinking IQ, which means like intelligence quotient, or it means the Japanese version of the or the Chinese version of the N64. But anyway, okay, fair enough. I need to spray stuff down. Read the board, please. Yes, that is true. Report cards go out tomorrow. Now, I don't care about grades, but some of you might a little bit more than me, which means if you're worried about report cards, you need to meet with me if you have. If you're not worried about report cards, that's fine. I don't care either. Report cards aren't final. Right? Yeah, I'm available after school. Yesterday I tried to meet with people online that wanted to make up for...
I don't like talking to people online.
You don't like talking to people online?
Nope.
Yeah, the internet's a pretty crappy place.
Sorry, I wasn't in class.
That's fine. You gotta do what you gotta do.
Google meetings and ask people.
Okay. I forgot to publish stuff. You don't have to. I understand what you're saying. If not liking it, sorry. Would you, and again, you may answer honestly, you know, your opinion matters. Would you be interested in trying out Google Meets once with me, just to see how it rolls? Because eventually we're gonna have to go online, probably. Yeah, oh yeah,
Okay.
Yeah. I figured that if you tried it, you'd be okay, but again, you know you better than me. Also, guys, check it out. I got my cameras all set up. I've got the crappy one that the school gave us for free, which again, I appreciate. But I also have the soundboard set up where it can switch back and forth. So check this out. Right? It's a little crappy, as you can tell. It flickers in and out. Eventually, I'll replace it with one of my own. But you can be on camera if you wanted. All right, before we do anything today, I'm going to catch you up on what we did yesterday. I try to assume that you guys weren't here the day before. However, I won't be teaching it. I'll just be recapping it. And there's a difference, okay? And I apologize for that. If you want to go back and learn it, I would advise you to go and watch the YouTube videos. Like, Rowan was gone yesterday. Excuse me. Wasn't able to make it. Totally fine. Don't care. I'm not going to try and be like, police you or something. Because I can't and I don't want to, right? Ooh. He's on basketball team.
Yes.
Left bench. All right,
Yep.
Anyway. If you miss, for some reason, go online and check out YouTube. You can watch the video later. So if you're like, oh man, I was busy all day doing something like sleeping, or whatever. I didn't mean to look at you and imply that. I just meant like if you were, God bless you. I went to bed at 3 a.m. last night. I wish I was able to do that.
Went to bed at 5. Woke up at 6.
And so, and I know that's just how teenagers be, right? I get that, right? If that happens, go and watch the video at your leisure. But just make sure you do, because it's good to write stuff about in your portfolio, right? That's the end-all be-all, more or less. And if you're missing days of class, you're going to have less of an understanding, and it's going to be a lot harder to write. So, but if you could pull it off, good for you. Yeah, Nevaeh. Of course, yeah. All right, so take a look at that while I'm doing attendance. Hey, Steven. All right, so I see Lindsay. Hi, Lindsay. I want to say your name is Lindsay. Lindsay? I don't know. I want to say it with like an A after the S. Because I know that's how you spell it, and my brain works on spelling. You'd think it works on numbers, but it doesn't. Skylar, ¿dónde está? Maddie, don't see Maddie yet. See Carter yet. See Josh. I see Rowan. Hey, Maddie. Maddie with the chevron zigzags and like the teal. Very trendy. Maddie, do you want to be a teacher when you grow up? I hope not. Don't do that. Don't do what I did. Don't make the same mistakes as me. Don't make the same mistakes that I did, son. If you are, we should talk about that. Max is here. Cliff, not here as far as I can tell. Nevaeh, Adam, Steven. Okay, and Adam is here. So anyway, we're taking a look at this to begin with. For those of you that are just checking in, I have a board camera now, which flickers. But eventually I'll bring in my wide camera, and that'll be the thing. Once upon a time, I was going to spend $400 at the beginning of last year to have a camera that followed me around as I moved around the room. All you gotta do is wear like a little thing, and it like follows that. And then if you hit a remote button, which I'd have in my pocket, it would know to automatically turn a certain degree and zoom in on a section of the board. Like I could program it to do that. It would have been dope as hell. Problem is that I didn't have $400 and I had to buy a lot of other stuff to get this up and running, right? Not this, but regular school. And I was very poor because I hadn't had a paycheck in a long time before I got this job. I put it off, and then coronavirus happens, and like, well, I don't need that camera anymore because I'm at home, right? I don't need a camera that follows me around. Man, now we're here.
How'd it go, Bob?
I know, that was the joke last year, right? Skylar's here. Carter's here. Awesome. So yeah, I will. Maybe I'll get one of those. But for now, I think with the board switching, this is actually a pretty good setup. Right? I think this works more or less. Because I like to run around and walk while I'm teaching because, one, your boy needs to lose some weight, and two, I'm much more energetic and much more entertaining when I'm moving around the room and doing things. Like, Lily knows because she's my student. So Lily, though, one of the people in chat, is a former student of mine. She's in college right now for math. She's basically acting as a student teacher unofficially, kind of observing stuff. Yeah, she wants to be a teacher. Don't do it. Or actually, you don't want to be a teacher necessarily. You want to do math, art stuff. I don't know. We got to talk about it. But anyway, she's in chat. She knows how crazy it was when I was first teaching in Sandwich, Illinois, my hometown, and how I would like run across the room and slap the board, and then run over to the other board and slap it over there, and like draw their attention to different things. I taught her calculus. That was a wild event. But anyway, yesterday we talked about shapes. All three flavors of shape. We have the square, the rectangle, rectum, I barely know him, and then the third one, which is the other flavor. It's like Diet Dr. Pepper. Okay? I prefer the third one, not because it's Diet Dr. Pepper. Maybe, I don't know. I'm not a big soda guy. I drink this in order to sustain myself. All summer I swear off of it, and then I swear off of it for the first 3 weeks of this school year, and then broke down. All right, so I would help special education students, but max out the students I can help and not be limited to a school district. Gotcha. So maybe work as like work for an outside organization. I did that for a while. I do that during the summers. All right, so at least when it's not coronavirus. So yesterday what we talked about was the first one, and I'm gonna draw a picture. Now, if this problem was a different problem, it'd be a lot easier. And I want you guys to get in the habit of thinking of a similar problem. That might give you insight, right? If I told you that this much, this is a square, right? You guys know a square, all sides are equal? Okay, wonderful, wonderful. And I told you this is 7, and I said, what's the perimeter? How would you do it? 7 times 4, or 7 plus 7 plus 7 plus 7, right? Ain't no thing. Now, how do we know that this and this is the same? Even if I told you it wasn't a square, how would you know that this and this has to be the same thing? Let's pretend it's a rectangle. How would I know that and that's the same? What? Measuring. Ooh, good idea, right? We get out this and we do this. Now, what is measuring? Right? Somebody made up these numbers. This one's 36 inches. No jokes. All right, so. No jokes. Someone made that up. Now, even if it didn't have 36 on it, pretend that this is my ruler. Do you know how long this is? No jokes? All right, so if I hold this up to this, we know that they're the same, right? I don't need to know what their value is. 5 centimeters, 12 feet, whatever, right? Doesn't matter. I know that they're the same because, look, I can put them up against each other. That's why we do that with the ruler. We put it up against something, and we're able to see that it's the same. Now, this has different marks on it because imagine I wanted to know how long something was for 12 inches, right? No jokes. Imagine I wanted to know. Would I need a 12-inch ruler to do so? No, I can have this guy and then just say, look, a 12-inch ruler would cut it off here, right? That's the idea. This is all a lot of rulers all in one, right? And that makes it useful. So I know things are the same length by lining them up. And just because this has numbers doesn't make it special. It's just saying, look, a ruler of length 12, like 12 little rulers put together, would be here, right? That's all it's saying. How long is this? Well, it's one Sharpie long. I don't know, new unit of measurement. Measure anything. And this is useful. Why? Because in imagination languages, where all these shapes exist pretty much, right? We're not measuring a literal square or rectangle here. I didn't draw this to scale, right? I have to bust this out all the time.
Take it easy, it's just a drawing.
Right? It's not drawn to scale. It's a drawing of a rectangle. I can't measure it because when I use my imaginary ruler, well, what's an inch, right? All I know is what I already have. I can use this to measure it. How do I know that this has to be the same length as that? Yeah, they line up parallel, right? They're like this, and they line up together. See how this stops exactly where this is? Now, we are doing a little bit of assuming here, and I talked about that yesterday, what assuming does, right? It makes a out of and. I'll do it one more time. My English teacher used to say this all the time. Assuming, you know what it does to us? It makes a out of and, right? But we have to assume a little bit that this lines up with that because that's how the drawing is drawn. Okay? So this also has to be 7, doesn't it? And if I told you this was 6, then you know that was 6. On and on and on. Boring. I know. But then I'm going to give you number 3. And you lose your minds. They always do. You think you're all hot stuff, and then you actually get thrown in the game, and you're like, oh no! You. Kobe. The Iceman from downtown. I feel like I deserve this.
Oh, jeez, you scared me.
That's right. I just do it for the love of the game. I don't want to get paid. Just for the love of the game, you know? They offered me a contract. I was like, no, man, that becomes a job.
I have to go to school early.
Because I'm just nailing them from all over.
Ron just went up to see Mom.
All right. How do we solve a problem like Maria? And why is it more difficult than the one we just solved? Maria is the first problem on here. They give you this little thing, and they tell you this much is, what do they say? 7 centimeters. Centimeters really doesn't matter that much in imaginary land. Centimeters is as good as a foot. No jokes. All right. They give you this. And they tell you it's a square. How would you find the perimeter of this? Where are your gods now? Well, yesterday what we said was this. We said that if you have an L, which is what this kind of is, right? You can take the pieces of anything that you have, right? And you're allowed to take them apart and put them back together again and have it be the same length, right? 4 pieces like that is the same as 4 pieces like this. I can rotate it. Same thing as taking it apart and putting it back together, right? You can just think of it as rotation or just taking it all apart and put it back, right? Those are the same. Now, how do we know that? Right, before it's like, oh, well, we lined them up and they're good to go, right? Okay, sure. But how do we know that this L is the same as this L? Well, they both have 4 pieces in them, right? That's what we said yesterday. We said you're allowed to take those pieces, divide them up, and then put them back together again. Now, there's no way to prove this, that this works. However, I think we agree that it should. It's hard to live in a world where it's like, well, I don't know what to believe, so I don't do anything. Actually, it's not very hard at all. It's very easy. You just don't do anything, right? But it's not very interesting or very fun. Mathematicians are about interesting and fun. They're not about what's always 100% true. In fact, we know with certainty, there's a theorem that says there are things in mathematics that are true that we'll never be able to prove. That means at some point we have to take a leap of faith. All of math is built on leaps of faith. It's not this exact science that people portray it as. Theorems are proven by other theorems, and those theorems are proven by other theorems, but eventually you get a theorem that can't be proven by any other theorems. It's the OG, right? And so what is it proven by? It's proven by postulates. Postulates are things that have to be true. They're not provable, but they must be true. Otherwise, we wouldn't be able to do math, and we'd rather do math than not do math. Because math leads to interesting things, like, putting a man on the moon. We call those postulates. They're kind of assumptions. But we know they have to be true because if they weren't true, it'd break all of math and we wouldn't be able to do anything interesting. And one of those postulates is called the segment addition postulate. Segment means pieces. Addition means adding them up, right? It means
Adam.
right? If you're in my second hour class, you call it Corinne's postulate because Corinne actually came up with this. Euclid beat her to it, by like a couple thousand years. And he called it segment addition postulate, SAP for short, SAP. And it says, look, you're allowed to break up any piece of line into segments and add them back together however you want. And when you do so, it should be the same. Right? Kind of like when you add numbers, 1 plus 2 plus 3 plus 4 is the same thing as 4 plus 2 plus 3 plus 1. Right? You can take these pieces, these 4 pieces, rearrange them, and it'll still be the same length. Am I blowing anybody's mind there? This is really useful because I wouldn't be able to measure my classroom unless I had a classroom-sized ruler, if that were true, right? Because I had to put these back to back to back, stick them together to measure the classroom, right? I head out to Ace Hardware, and I'm like, hey, I need a ruler. They're like, okay, how big is your classroom? I say, well, I don't know. It's like, well, we can't give you the ruler that's the same size as your classroom until you tell us how big your classroom is. Wait a minute. How am I going to buy a ruler to measure my classroom? It has to be the same size in order to measure it. I don't know the size. You see what I'm saying here? Right? It's very good that this is true, because then I can measure my classroom with anything. I measure it with my shoe, I can measure it with Sharpie, I can measure it with this. I don't need to have an exact measurement tool to do it. I can break it up and stick them together, and I get the whole length. Hopefully this isn't blowing anybody's mind. But how do you solve a problem like this? What about this? Where are your gods now? That ain't an L. At least it's not L of the same kind. This is a different kind of L. What's different about this L? It's 2 and 2, not 3 and 1. You say it's the same thing. Why? Yeah, it's the same number of pieces. It's 4 pieces just rearranged. It's segment addition postulate. We're allowed to do that. So it turns out not only is rotation fine, but breaking it up into different pieces is totally fine too. As long as we put it back together, it'll be the same length. Those are all the same. We cool with that? So if this is 7, we know that since that's the same, this is 7. And we know that this must be 7 as well, and the perimeter is 7 plus 7 plus 7. 5 plus 5 plus 5 is 15, plus 2 plus 2 plus 2, that's 6, 21. I don't know. Or 10 plus 10 plus 10 is 30, minus 3, minus 3, minus 3, minus 9. 30 minus 9, 21. I don't know. You do your thing. Excuse me. Next. Number 2! I want you to write about this in your portfolio, by the way. This one's a mandatory one. All 3 of these. Hopefully the first one made enough sense. The third one, you're going to be iffy on. But I want you to give it a chance. So, for number 2, they don't give you tick marks on all of them. Tick marks, that's you. Tick mark. You're a tick mark. Your mom ever call you that? Okay. I'll have to tell her that in the conference. You have a brother named Mark? Yeah. Okay, you're destined to have a son named Mark then. Tick mark. Okay. Do it for me.
I will.
When I'm up in heaven, dead, I died at like Kobe's age because I became a star and I was on a helicopter or something. Be like, this one's for you. And I'll be looking down and be like, yes. All right. They tell you that's 18. How are you going to find this? How are you going to solve a problem like Maria? No magic. Magic isn't real. Hogwarts is not real.
Don't hurt me like that.
Hey, you know what? We've had some, it's okay. It's okay. We need to move on beyond Hogwarts. Time travel exists. Let's give it to students so they can learn how to, do magic. Oh no, the Dark Lord is attacking. Whatever will we do? He killed a bunch of people. Well, nothing we can do about that. If only time travel existed. J.K. Rowling, what a great writer. Okay. Don't get me wrong, I enjoy the books. Where are your gods now? What are you going to do about this? So you're saying this and this is the same?
Yes.
The red and the blue? That makes sense. They're both 4 across. How do you know this is 4, though? We don't have tick marks down here. Aha! Works out. This must be the same as that, right? Has to be. And we already know these are the same. Okay, cool. What about this? Well, yesterday, we talked about relationships. Okay? I'm going to write this, and you're going to go, what? Oh my god! Ah! How do you solve a problem like that? I bet some of you have screwed up a problem like this before. 4 divided by 2 equals 18 over x. Ah! No. Division. Here's what I want you to think about. Division is relationships. Division is about relationships. You might think, oh, no. Division is I have 4 M&Ms and I have 2 friends. How many M&Ms did everybody get? And that's true. That sometimes works. But you know what's really true about that? It's sad. You have 4 M&Ms and 2 friends? Good God. You have more M&Ms than you have friends. And you only have 4 M&Ms. Get help. We need that Michael Jordan thing to pop up. You know what I mean? The thing. Yeah. Stop it. Get help. Get some help. I need that. Remind me. Okay. No. Do not read 4 divided by 2 equals 18 over x. Oh my God. What? No, stop. Please. No. Make it stop. Division is relationships. I want you to read it like this. The relationship, because that's what division is, right? The relationship. No, math class. The relationship between 4 and 2. I'll say it again. The relationship between 4 and 2. The relationship between 4 and 2. Think about how they relate. Is the same as the relationship between 18 and 1. Adam, 4 and 2 relate the same way as 18 and 1. Think about the relationship between 4 and 2. What does 18 relate to in the same way? 9! Do you guys see? I don't need to cross multiply and all that crap. Oh my God, please don't. We don't cross multiply in here. Talk about that later. It doesn't work. It's a lie. 4 is the same as 2, relates to 2 the same way 18 relates to 9, right? Namely double. How do we know it's double? Well, because I know 4 and 2, right? But what if you didn't? 4 divided by 2 is 2, yeah? What's 18 divided by 9? 2. See how they have the same relationship? Division tells you the relationship. Maybe you didn't know what 100 divided by 50 was, right? Or 150, how they relate. Well, if you do 100 divided by 50, you get 2. It shows the relationship. There are 2 50s in 100. There are 2 2s in 4. There are 2 9s in 18. 4 is twice as big as 2. 18 is twice as big as 9. It tells you the relationship. That's what division is. Now, some relationships is meant to be. You know what I mean? You and your crush is meant to be, right? You fit on so many levels. Shoot or shoot, right? Some relationships, though, you're like, girl, why are you dating him? You could do better. And she's like, I know, but like, he's hot. And you're like, yeah, but like, he's not good for you. And she's like, well, I'm not really that good either, okay? Right? I'm not so good either. And you're like, Sarah! I know. Right? I used to have a nephew, long story. Used to have a nephew named Elliot. And his mom is very new age. Move on, okay, later, that's not important, okay? His mom is very like new age, hippie, cool, like vegan, right? And I don't think she told him to say this, but because she says it, I think he picked up on it. If you offer him something he doesn't like, here, Elliot, you want to eat some broccoli? He won't say no or no thank you or any of that. Here's what he says. He says, that's not right for me. That's not right for me, right? It's very new age, right? He's not right for you. And then when I show you this, that's not right for me. That's your response. That's not right for me. I don't like that. Gross. Fractions. Ew, gross. Here's the thing. It ain't that bad. You like fractions. Here's why. Because fractions are easy answers to difficult problems. And you like easy answers to difficult problems. This is an answer to the question of, how do 5 and 7 relate? Or in other words, what's 5 divided by 7? Now, Nevaeh has a calculator. She was just on it doing the math, checking that. Nevaeh, would you check what 5 divided by 7 is for us? Okay, and is that the complete answer, or do you not know? Does it stop like, okay, you ran out of room? So this might be the right answer all the way, or it might be an estimation. Your calculator might have rounded, right? If you get an answer that goes on like that, eventually they're going to ask you to round too, right? Right? You have to be like 0.714, right? Now, when you round, you are estimating, correct? It's not the real deal. It's close enough, right? So you're telling me, and I asked you to do this, so this is not your fault, but you're telling me you got out a calculator to get an estimation? Dude, I can estimate. What's 5/7 about? Well, it's less than what? 5/7 is less than what? Five sevenths, what's it about? It's less than what? Let's estimate. 5/7 is less than what? Less than 100, very good. Let's get a little bit closer. Less than what? Less than what? Take your time. What's it more than? More than half? Yeah, makes sense, right? Half of 7 is like 3.5, right? So it's more than half. And it's less than 1, right? So it's like 0.6, 0.7, 0.8, 0.9. I don't know, probably not 0.9. Maybe like 0.6 or 0.7. I did that in my head and got close enough. You had to get out a calculator to get this and round it anyway. Now imagine you type in the calculator wrong, right? You hit 5 divided by 71 on accident on your way to hit the equal sign, and I'm looking at the decimal going like, how in the world did they get this, right? Why waste your time and energy on that phone when you could instead just say, look, you know what 5/7 is? The exact answer is 5/7. 5 divided by 7 is 5/7. How does 4 relate to 2? Here's 2. How does 4 relate to it? Well, here's 4. Isn't it clearly double? How does 5 relate to 7? Should need 8 dots to make 7 segments. And then 5. 1, 2, 3, 4, 5. Well, it's less than 1, a little bit more than half. I'm estimating anyway, right? Well, I need an exact answer. Great, I have great news for you. 5 relates to 7 in this way. 4 is double of 2, right? 4 is twice as big as 2. 5 is 5/7 of 7. Isn't it? Isn't it 5/7 of 7? It is. It's 5 out of 7. 4 is twice as big as 2. 5 is 5/7 as big as 7. Being 5/7 of something is less than the whole thing, right? It's 5/7 of it. It's exact. That's what it is. That's the relationship. I'm 5/7 of what you are. I'm double of what you are. Some relationships are really great. 5 and 5, how do they relate? They're one and the same, right? I'm exactly what you are. Aww. What we call a mutual relationship. Some of you guys are in a 5/7. Other you guys way out of your league. Girl, You could do better. Some of you. 5/7. It's an easy answer to a difficult problem. What's 5 divided by 7? Oh, let me get up my calculator. It's 0.71428, right? No. It's 5/7. Oh my God, how'd they know that? They're geniuses. What's 99 divided by 4? It's 99/4. What? Seem like a genius. Unless the one kid catches on. Wait a minute. It's just the same as a what? Why didn't they tell you this? Now, adding fractions can be a pain in the butt. I agree, right? But we're not doing that. We're talking about what fractions are. Fractions on their own aren't bad. Adding fractions, we'll talk about it. Fractions on their own are great. 5 divided by 7. Oh, it's a 5 remainder. No. 5/7. Done. Exact, perfect every time. 4 divided by 2. It's 4/2. Well, there's an easier way of saying that. 2. You're real stupid, right? I don't know. So why am I talking about this? I'm talking about relationships. 4 segments and 2 segments have a relationship. What's the relationship? Well, it's going to be the same as 18 is to whatever this is. 9. How would you add those numbers? 9, 18, and 18. What would be your strategy for adding them in your head? How would you?
Adam.
How would you add 18, 18, and 9? 20, 20, and 10. And then subtract 2, and subtract 1. That's 5. 20, 20, and 10 is 50. Minus 5 is 45. Boom. That's a good way. That's how I do it. Maybe I do 10 and 10 and get 20. 8 and 8 is 16. That's 36. 36 plus 9 is 36 plus 10 minus 1. Or maybe you know 9s, right? 45. 36 plus 9 is 45. Moving on! Number 3. This is the one that you're not going to understand, right? You're like, easy, boring, whatever. Okay, we talked about fractions for a bit. Sure. How do you solve a problem like Maria? They don't tell you it's a rectangle. They don't tell you it's a square. They do tell you it's the third option in shape world. Now, notice that A, that little segment going down to A, kind of looks like it's a little segment that goes down further again, right? It's like here and here. This little guy does not look the same as that. Again, it's all imaginary. This is a stretchable shape, okay? We only know stuff that directly sits above another. Josh, what do you have to say? I like what you're thinking. I'm going to get to that in a second. Before I do that, this is how they've labeled it. They had a B down here. There's a B, right? But I'm going to put it here so we do alphabetical order because it's easier to talk about this if we know the segment names, right? Talking about that segment right below A is kind of like, okay, which, what? I don't know. But if I say AF, you know what I'm talking about, right? AF? No? Okay. 13 centimeters is the length of the red parts. Not just this, but all of that, okay? So Josh is saying, can't we do what? Explain. So Josh is saying, look, I can add this in to make it a rectangle shape I understand, and then I can subtract it later. Okay, that makes sense. That's one way of doing it. So now what? What would equal 13? Can you give me letters? A through C. So A going like this, or A going like this, or A going like this. So AC can mean different things, right? Give me some letters. A going to, F going to, D. Oh, wait, you want to go to here? Let's put this, let's do G. So AFGD or AFED? Okay, here to here. So AGC will work. We don't even need to say F. So AGC. Segment AG, we'll do that. Okay? Plus this guy, right? AG plus this one? GC, what about it? 13. So you're saying it's the same as this. So let's write that. AB plus BC. Now, how do you know that to be true? What's parallel to what? Okay, so in math class, we use tick marks. Okay? This is kind of helpful. AB it's the same as GC because they sit over each other. I'm going to use a tick mark on this so you know it's the whole thing and not just that. Okay? So those two go together. They're the same. Do you see why they have to be? They line up. Are we cool with that? Right? And then Josh says that this has to be the same as this. Right? Because they line up. Does that mean that this is the same length as that? No, not necessarily, right? Because they don't line up. But we know for sure this is the same and that's the same. Is this a rectangle? Is it a square? I don't know. Right? But I know that this is the same as that, that's the same as that. Okay, I'll buy it. So you know that the blue must be the same as the red because this piece and this piece both match up with the piece over here, right? So we know that these are the same. This is true, which means they equal 13. But here's the problem. I don't want this, I want this. How do we line them up? We want these pieces, right? What do those line up with? Because again, that's how we have to measure things, right? We can't bring in a separate ruler. We have to see what they have already lined up for us and use that to measure. Josh, go ahead. Give me a letter. F-E, this part right here. You can add points if you want, right? There's a point above E on line AB, right? Let's call it, instead of H, because H and I, if you rotate them, they look the same, capital, right? So J. You're saying this is the same as that? Okay, so let's use 3 tick marks. Everybody agree with that? Disagree? Agree? This has to be the same as that, right? Because they line up, right? Okay, good logic, good logic. Okay, this one right here. Yeah, we gotta do this, right? So, okay. Now, question. Is BK half of BC? Why? Is BK half of BC? How do you know? How do you know it's half? Pretend this was 10 in length all the way across, B to C. How do you know it's 5 and 5? Do you? Couldn't it be 2 and 8? And you're like, but it looks like half and half, but I need to remind you.
Take it easy, it's just a drawing.
It's a drawing. Because it looks half and half doesn't mean it is. Now, if you lined it up with something, right, and you're like, oh, and here's why, right, great, that's good reason. But just, well, it looks like half. That ain't gonna cut it. It might be half. You might be right. But that's not gonna be enough evidence. You see why that isn't enough evidence? Okay, no yelling in math class. So, Josh says this is the same as that, and this is the same as that. Great, but I don't know how long these are. I don't know if this is half of whatever, right? Maybe this is 3.25, 3.25, 3.25, 3.25. I don't know. So this would be 6.5, and this would be 6.5? Rowan says yes. Why? Why is this 6.5? Why? Not necessarily. We need to get used to saying that, right? It could be, right? It could be. If I tell you we have x plus y equals 10, does that mean x and y are both 5? No. Could they be? Oh, yeah, sure. This and this adds up to 13. That's all I know, right? This could be like 0.1 and this could be 12.9, right? I don't know. The drawing. So we don't know that this is 3.25, half of 6.5, right? But we do know these are the same and these are the same. That's good. What else do we know? This much is 13. This much is less than 13, right? What are you saying, Josh? BC. These two add up to BC? How do you know that? This one I can see because it goes across. Are you flipping it? Okay, here's the thing. How do I know that's the same as that to be able to flip it? How do I know FE is the same as JE? Do I? It's not lined up. Do you see? Are we seeing that? It is just as important to see why something isn't true necessarily as it is to see, oh, I know what the reason is, right? Or I see the answer. Why is FB not necessarily the same as JE? Because you'd have to rotate it to get it there, and we don't know if that's the same. I want you to work on this some more. Write about it. First two you should be able to knock out on here and explain what those are pretty clearly and thoroughly. Use pictures. Be thorough. The third one, give me your best attempt at logic through it. You guys did some good job. Did a good job on this day. Go back and watch the video if you want to recap on it. Okay. Write about this. Bye.
I still thinking about my portfolio. I mean, I forgot to publish it. I just published it, and then I'll talk to you probably after school today.
Okay, send me an email or show up. Yeah.
So can I
Yeah, you're more than welcome. Make sure you have your Chromebook and ready to go because I want to record the meeting so I can put it into Skyward. Is that okay? It's just for you or your parents. Okay. Rad.
And then tomorrow, I'll be. That's why I had to.
Yeah, that's fair. Sure. When it does work, watch the video.
I will.
Okay.
Or I can log in on my phone. If my phone.
Yeah, whatever you want to do. Okay. Thanks, Avea. Yeah, I'll mark you here regardless. All right, so I didn't have Cliff. That was it. Next hour. Hey, Logan. Stick around, guys. We're going to be writing about something today.
Oh, it's cold in here.
I need to recap what we did yesterday. Sorry, people online, that we have to do the recap. Eventually, I'd like to get to the point where I don't have to recap the day before, and I just assume you guys were here. And if you missed class for whatever reason, internet, sick, etc., that you went and watched the video at your own leisure. What's great about YouTube is if you click the gear, you can actually speed it up. You know that, right? You can turn it on like 1.5 speed, and I'm mostly understandable at 1.5.
There's days.
There are days. There are days. Oh yeah, let me wipe it down. Sorry guys, it's not. Unless someone hits the last hour.
Yeah, no,
it's
it's
not
not.
great. Sorry.
So,
Guys, I got a new camera set up now. That one right there. The school got it for all the teachers for free. Mine, for some reason, glitches out. Like it switches. So I'm going to bring in another camera to replace it, but we have a board camera. I do the board camera.
I just wiped it down.
Good? Oh, sorry. So,
Backpacks are back, and I come after school.
yes. Make sure you bring your Chromebook because I want to record the conference so we can put it up on Skyward, okay? They can now. I also got this working so I can switch between stuff faster.
Hey guys.
But yeah, not a great camera. As you can see, it twitches. Right? Oh, don't touch it. Don't touch it. Okay.
You get 10 minutes.
right here,
Right
Jamie.
there.
Oh! Is my face in it?
No.
Oh,
Then I can switch back and forth between computer, my desk, and this.
Jamie, you're there.
I'm going to leave this while I take attendance. That's what we're going to be talking about today. We did the first two yesterday.
Review because I've been trying to ask you in class because they kicked me out of that one after I was doing everything.
Dude, it's been like 3 weeks. Like,
I didn't do program before I left.
it's been like 3 weeks since we like got on that. That's not good. Have you been writing anything outside of that? Like, I don't know what to do for you, man. Yeah. Are we gonna have something to talk about today or no?
I'll write it.
Okay. I'm gonna give you for 3 weeks.
Yes,
But
Jamie.
give it a shot.
Salted by hand.
It's okay. The thing is, the grade isn't permanent, right? So you can go back and do more on that stuff, and eventually get it up. But while I'm taking attendance, take a look at these guys. We did the first two yesterday. We have all three flavors of shape up there. We have square, rectangle, and that guy, the Diet Dr. Pepper of shapes. See, I saw Logan. I see Jackson, who's got the new profile picture. Yikes. And then Troy looks like he's ready for Halloween. Troy, Maddie. I see Mitchell. I see Olivia. I don't see Cooper yet. Am I missing Cooper? I don't see Isaiah. I see Ann. No Zach, as far as I can tell. Dina. And I see. Do I see Jordan? I do see Jordan. Jamie's here. Anybody see Engage? What about CJ?
No, I haven't.
All right. Well, we got everybody else. I will submit attendance later towards the end. Just make sure you tell me you're here if you're coming in late. We are going to recap yesterday. I apologize for that. Eventually, we're going to get on the rolling, so I assume that you're here before. My advice is if you missed class, whether you're sick, you didn't show up because you were sleeping, write online, or whatever the reason is. I don't care. I'm not going to try to police you. I don't want to. I can't, even if I did. I would encourage you to go and watch the video from the day before up on YouTube. and watch it on like 1.5 speed or something if you really don't have time. But get an idea of what we're doing the day before. That way I don't have to do a giant recap. Today, I'm going to do a pretty big recap. So, what we talked about were these three. Again, all three flavors of shape: square, rectangle, and that guy. The first one, we talked about this. Let me draw it. And they tell you it's a square, right? They break it up like this into different segments, right? Segments mean pieces. And an easy problem was if they said that this whole thing is 7. What would be the perimeter if this whole thing was 7? Here to here. 7 plus 7 plus 7 plus 7. 7 times 4, right? Ain't no big deal. But the problem is, they give us this L shape and say it's 7. How do you solve a problem like Maria? Well, yesterday, what we said was that, look, this is 4 segments put in an L, right? It looks like this. There we go. And we're saying that should be the same as if you take those 4 segments and just rotate them to this. We talked about rotational symmetry, right? Things are the same after rotating. That's called rotational symmetry. Your boy is not rotationally similar. Let's see if I can do this.
Oh, I'm terrified.
Okay. Your boy is not rotationally similar. So if I stand here, right? My face is up here. And if you rotate me 90 degrees, I'm not similar. I'm not like
Lexi, do it.
Lexi, do it.
Lexi.
Do it.
Lexi.
Show us that you're not rotationally similar. Can you stand on your hands? I'm seeing stacks. I do it on camera. Wow, that was amazing. No one saw that. Okay, so anyway, I'm not rotationally similar. Hi, CJ.
Welcome, CJ. You're late. I miss you.
I don't know if you heard that, but she said she misses you. Demery says she misses you. All right, so these are rotationally similar in the sense that they end up being the same before and after. So let me show you what that looks like. These two, right? Doesn't matter how they're rotated, they're going to be the same length. Now, how do we prove that? We can't. We cannot prove that. This is actually one of those things that you have to take a leap of faith on. Andrew's got the calculator out. He's like trying to figure out, are they the same? Are they the same thing? They are. You don't need the calculator. You're fine. So, what? You what? Yeah, me too. You checking like 5 times 5, making sure it's 25? I appreciate that. Tell me if it changes. Oh, she misses you too. Hey, Cooper. You mark your her. Yeah, yesterday we said this L is the same as this L. Why? Because they're both 4 segments in length. And we know this segment's the same as that segment because they're right across from each other, right? They have to be the same. And these 3 segments have to be the same as this, and on and on and on and on and on, right? And it's a square, so we know these 3 are the same as those 3, et cetera, et cetera. These have to be the same. Now, where are your gods when it comes to this? Why is this one a little bit more different than the other 2? I think you guys can agree pretty easily that this L and this L are the same, so they're both 7. What about this guy? Why? Yesterday we talked about how it's totally fine to take pieces of something, take them apart, and put them back together. It'll be the same. This makes sense. Yeah, it's still 4 pieces, right? So not only are these the same, but also this would be the same, and this would be the same, right? They're all going to be the same. It doesn't matter if you take them apart and put them back together, it's still going to be the same. Now, there's no way to prove this. And that's okay. We don't want to have a lot of things where like, dude, just trust me, right? Because eventually, like, it's all just made up, right? But mathematics at a certain fundamental level is. There's actually a theorem. Theorems are things that are proven, right? There's a theorem that says, it's called Gödel's incompleteness theorem. Incompleteness. And what does he talk about for incompleteness? Bless you. Yeah.
About math is I just have to do something.
Yeah, exactly. That's what we talked about yesterday. So these leaps of faith we call postulates. And we try to have as few postulates as possible, right? Because a lot of leaps of faith eventually are just making it all up. But this one we cannot prove. And mathematicians are interested in stuff that's interesting. Right? They're not like my mom who's just like, well, I can't tell one way or the other. He says this, he says that, I don't know, I'll just stay home, right? That's fine, but it's not very interesting. Mathematicians are like, look, man, we can do a lot of really cool, interesting stuff if this is true. I'm willing to say it is, and that it's just one of those things we have to accept. Depending on who you ask, there's 4, 5, or 6 different postulates in geometry. 6 different leaps of faith at most. Everything else, we know for sure. It's either proven by other theorems, saying, look at this theorem, that proves this theorem. Or we say, look at this postulate, the OGs, right? And that means this. So these are the building blocks, the absolute foundation of our geometry. The first postulate we're going to learn about is the segment addition postulate. If you're in second hour, you call it the Corinne Postulate, because Corinne came up with it, actually, just 1,000 years later than Euclid. But she came up with it the other day, actually. Like, it has to be, because of this, this, and this. The segment addition postulate, I like this one, because for short, it's SAP. That's easy to remember. And it says that, look, segments, you can break something up, that's what a segment is, right? And you can add it back together, and it'll be the same. Doesn't matter if you add it back together like this, or you add it back together like that, or add it back together like that. It's the same. Are we cool with that? Am I blowing anybody's mind? Am I blowing your mind? This should make sense, right? If I want to measure a classroom, I can put these end to end to end and measure it, yeah? That's no big deal. And if I put these end to end to end to end to end against something else, and it's the same number of these, then they're the same length. Right? Doesn't change anything. That's how we solved this one. We said this also has to be 7. How would you add those three numbers? 7 plus 7 plus 7? What's your strategy? What?
7 times 3 or 4 plus 7.
Yep, 7 times 3, 21, 14 plus 7. If you really don't like 7s, you could do 5 plus 5 plus 5, plus 2 plus 2 plus 2, so 15 plus 6, I don't know. Another way to do it would be 10 plus 10 plus 10 is 30, minus 3 plus 3 and 3. 30 minus 9, 21. I like that one. All right, you're like, boring, obvious. I know, it's because we covered it yesterday and you were here yesterday. That's why it's so easy. Also, this stuff is easy. And then I'm going to show you number 3, and you're going to lose your minds, right? That's what happens. I set you up, you're like, oh yeah, no big deal. And then I'm like, okay, now, let's do something interesting. And you're like, ah!
You said so much fun, Tom.
I want to say, you like Krabby Patties, don't you, Squidward? The next one looks like this. Now, notice that this one doesn't have tick marks at the bottom. If you see Adam Tickler, call him Tick Mark. He loves it. He's going to name his first son Mark in honor of me. It's going to be a tick mark. So no tick marks here. And they tell you that this is 18 centimeters. How do you solve a problem like Maria? No, no magic in here. Sorry, J.K. Rowling is a lie.
She's a scam and a bad person.
Yeah, she kind of is. That's okay. We liked her books. There were obvious problems with it initially. Think about it. They have a time turner. They can turn back time, and they give it to a student to learn, like, magic out of school. She's like a third-year student. She's like 14. Here, mess with the whole universe. Turn back time so you can take an extra class. Meanwhile, millions of people die in a Holocaust started by Voldemort. And they're like, I wish there was something we could do about it. Sorry, Harry, your parents died. If only we could go back in time and save them. Too bad we can't. Oh, hi, Hermione. Here, have this. I enjoyed the books too, but there were obvious plot holes. Okay, so 18 centimeters is how long this whole thing is. Again, if this was just 18, easy. That's 18 too, right? But we got this L thing, so how are we going to do it? Yeah, good point.
They're terrible people.
That's the law.
They're wizards!
I know. Very inclusive. How do you solve a problem, Maria? We haven't even got to the hard one yet.
Well, the top should be the same thing as the bottom.
You mean this and this is the same, or do you mean the L?
L.
Okay, that's fine. That's segment addition, right? Now, but wait a minute. Before we knew 4 pieces is the same as 4 pieces, doesn't matter what shape they're in. 4 pieces here. How do you know this is 4 pieces? No tick marks. Yeah. We know this has to be the same as that because look, this and this are the same because they're right above each other. Now, think about this. How do we measure something? We put the ruler up next to it, and if it's the same length, then it's the same length as the ruler, and then we look how much that is. Now, what's nice about a ruler is it has numbers on it. I don't need to take this ruler and put it up to something that's exactly the same length to know, oh, it's 36 inches, right? I also have lots of other rulers contained in here. That's what these little numbers are for, right? Oh, look, it's the same as a 10-inch ruler. That means it's 10 inches, right? No jokes. Another way we can measure things is we can say, look, I don't know how long this pen is, right? You don't even know what color it is. Wrong.
Oh.
But if I put it up against this pen, you know that it's the same, right? Did I need to know that they're both however many inches long? No. And that's useful. We cannot bring a ruler into math land because your ruler might be different than mine. It's all imaginary.
Numbers are all.
This is true. But we can use rulers that are already in the drawing. And what I mean by that is things that we can put up to each other and say, look, see how they match? That means they're the same. I know this piece up here at the top is the same as this piece up here because they line up. Are you smelling what I'm stepping in? This lines up with this. They're right over each other. So they must be the same. That also means that this must be the same as that. Okay? So I know that this is 3, then that must be 3 pieces, right? And they're going to be the same. That L will be the same as that L because now we have 4 pieces and 4 pieces. But how do you solve a problem like this? Where are your gods now?
I don't have any.
Why is this harder to figure out than this?
Yeah, it's the same purpose.
It's the same length as this. But how long is this?
A third of. No, it's not. Hold on.
How do we know that these are all equal, these 4 pieces right here? We don't, right? We know these 3 pieces are the same as these 3 pieces because they line up. But how do I know that's the same as that? I don't. So I can't just do 18 divided by 4, right? I can't. I could, but it wouldn't be guaranteed to be right. True, but we want to limit those as much as possible. How do we figure out how long this is?
That's a down the bottom.
Sure. Let me think about that. You know what? For now, let's say that all of these are the same. That all these tick marks are the same. I think that's valid. That seems to be what they're implying. Let's do that. For now. So if all of these are the same, we can take 18 divided by 4, like you said, right? And figure out what these are. That's one way. I prefer to avoid division if I can, wouldn't you? If this is 18, how long does this have to be? Let's talk about relationships. Okay? Let's talk about relationships. You tell me. All right, so division. When I say division, if I say something like, I don't know, 14 divided by 7. Or let's do something different. Let's do 6 divided by 3. Right? You think 6 pieces of candy, 3 friends. I know what that means. What does that mean?
2 pieces.
No, what it means is you have 6 pieces of candy and only 3 friends. You're a loser!
Usually.
You have more candy than you have friends, and you only have 6 M&Ms. Right? Exactly. Get yours. All right, anyway. So 6 over 3 is 2, something like that, right? We think division is this idea of we split up the candy. And it's not wrong, but then you get negative numbers in there. And it's like, wait a minute. Maybe it's not really that. You know what it is? And then I'll tell you this. Division is relationships. It's all about relationships. Some relationships are nice, like 6 and 3. What's their relationship? How does 6 relate to 3? I don't want you to read 6 divided by 3. How does 6 relate to 3? Half, or double, right? 6 is twice as big as 2. Do you see how the answer to 6 divided by 3 tells us the relationship? 6 is twice as big as 2. What if I did it the other way around? It's not going to be 2 anymore. It's going to be 3 is half of 6. Oh my God. That's all fractions are. That's all division is. They're relationships. Now, some relationships are nice. You know, some of you guys are you know, you could do better. Like, honestly, 6 is twice as good as 3. Some of y'all could do a little bit better.
I would know. I've never done.
Right? Okay? Couldn't do worse.
You can well, like myself.
What up? Oh, it's going. We're just talking about relationships. You know how you got some people that are twice as good as their partner, right? It's not a very good relationship. 6 and 3 are like that. When I say division, I don't want you to think 6 pieces of candy and 3 friends, because that's just sad. You have more friends than that, right? You have more than 6 pieces of candy. You got a job? Yeah? You can go to the store and buy more than 6 pieces of candy. I don't want you to think divide it up. And here's the real reason. If I use negative numbers, that doesn't make any sense. Negative pieces of candy divided by negative friends. You see how that falls apart? It's a metaphor, and it works in elementary school, but that's not really what division is. It works for some of it. But really what division is relationships. When you see this sign, don't say 6 divided by 3. Say, what's the relationship between 6 and 3? Double, right? 6 is twice as big as 3. 3 is half of 6. That's all, man. Now, some relationships, right, 6 is twice as good as 3. You need, honey, you can do better, right? Get you a real man. Now, what about 5 and 5? Oh, that's the ideal relationship. What's the relationship? 5 is the same. 1 and the same. That's 5. Aw, true love. Mutual relationship. Now, some relationships are messy. Like this. 5 7s, right? That's a messy relationship, right? I used to have, don't ask. I used to have a nephew, his name's Elliot, and his mom is very vegan, like, you know. And I don't think she told him to say this, but instead of like, if you offer him a piece of broccoli, and instead of him being like, no thank you, or no, and he's like 4, here's what he says. You're like, Elliot, you want a piece of broccoli? You want to try some broccoli? And he's like, that's not right for me. That's not right for me.
It's broccoli.
It's very cute. It's not right for me. It's just not for me, man. It's just not my jam.
Understandable.
It's like, I gotta respect that. Like, he's conveying his feelings in a healthy way. And you're like, okay, you don't get me broccoli. That's not right for you.
Or his mom's.
Right? Sure. So, when I show you 5 7s, that's not right for me. This is a relationship you don't like, right? It's not right for me. That's what you say. But here's the thing. Fractions don't have to be that scary. Yeah, they suck to add. They really do. I'm not going to change your mind on that. There's a way to get around that, but I'm not going to change your mind. I might make it easier, but I'm not going to change your mind. Fractions are great because they're easy answers to hard problems. And we like easy answers to hard problems, right? You're like, wait, what? Yeah. Fractions are easy answers to hard problems. Lexi, you have your calculator out and you're already typing stuff in. Actually, Andrew had his calculator out earlier. Andrew, you ready to go? What is 5 divided by 7? I'm going to write this down here so I have room to write my answer. What is 5 divided by 7? 0 point. And that's where it stops? That's where your calculator cuts off, right? Keep going? Or is it done right there? That's perfect. Oh, great, wonderful. So, you're telling me you got out a calculator, and you did this because I asked you to, right? This happens all the time. In math class, like, what's 5 divided by 7? And they make you get out a calculator to get this answer. First of all, yuck. What does that even mean? Don't care, don't know. Write it down, get the grade. Second of all, your calculator had a round. Now, maybe it stops right there? Probably doesn't, okay? We're dividing by 7 here. So, you had to round. And rounding is estimation, yeah? Now, if you're on a job site, right, and they want an exact answer, can you get an exact answer here? No, because you're going to have to round eventually, right? So don't be like, well, sometimes you need an exact answer. Sure, you do, but, like, this ain't it. That's rounding, right? Sometimes you'll round to 7, sometimes you round to 1, sometimes you round to here, right? But it's rounding, it's estimation. So you're telling me you got out a calculator, typed it in, hopefully correctly, to get an estimation? Teachers make you do this. You're wasting battery life. How about we think about it for a second? 5 7s is between what 2 numbers? 5 and 7?
Wait, hold on. No, wait, stop. Hold on.
I'll stop, sorry.
How do you go then?
Okay. What is 5 and 7 between 2 numbers? Give me 2 numbers it's between.
Oh,
Sorry, 5 7s. Let me say it again.
Yes.
The fraction, 5 7s. 5 out of 7 is between what 2 numbers? Well, it's bigger than 0, right? Yeah, it's between 1 and 0, right? Can we agree with that? 5 7s is less than 1, right? So 5/7 is less than 1. She can do what she wants. If she's a nerd like that, wants to do math on her calculator, she's more welcome to. 5/7 is less than 1, right? Now, hold on. Is it more or less than a half? More, right? Because half of 7 is about like 3-ish, 4-ish, right? This is more than half. So it's not 0.5, it's like 0.6, 0.7, 0.8, 0.9. Probably not 0.9, that's a little too close, right? So maybe it's 0.6, 0.7, 0.8. Let's go 0.7 for the middle. Oh my god! Wow! I estimated in my head without using a calculator. I know it's more than half, I know it's less than 1. I don't know, 0.7? If you're gonna round anyway, might as well do it in your head and get on with your life. Instead of pulling out the calculator to get it done, wasting battery. But I need an exact answer, Mr. Mac! Great, fantastic, glad you're in my class. You know what the exact answer is? 5/7. No rounding needed. 6 is twice as big as 3. 3 is half of 6. 5 is the same as 5. 5 is 5/7. 5 is 5/7 of 7. Isn't it? Why didn't they teach you this? Oh, pull out your calculator, we're gonna get a remainder. What? No, what? No! 0 remainder 5. I'm smart. What does that mean? No idea. No idea, man. No idea. It's 5/7. 5 is 5/7 of 7. I'll prove it to you. 6 is double of 3 because here's 3, right? And here's 6. Yeah, it's easily double. Great. Fantastic. 5 and 5 is the same. I don't think I need to illustrate that. 5 and 7, how do they map up? Well, 7, we need 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. That'll be 7 line segments, because every line segment needs 2. Isn't 5 less than 7? It's 5/7 of 7. Are you smelling what I'm stepping in here? It's 5/7 of the thing. That's the answer. Fractions don't suck. Your teachers do. Why are they making you... What the... No. God, please, no. That doesn't mean anything. You're out on a job site measuring. Okay, I need 5/7 of this board. Okay, that's 0.714 inches for every inch. What? It's 5/7. Divide it into 7 pieces. Take 5 of them. 5 divided by 7 is just 5/7. Fractions are division for lazy people. I'll say it again. Fractions are division for lazy people. I am lazy. I like fractions. Do I like adding them? It's not as bad as you think. But talking about them? Oh my god! Less than 1, more than a half. 5/7. Now why are we talking about this? Because fractions are relationships, right? Division is relationships. I know this much is 18, this blue part right here, right? That's what they said. And that's 4 different pieces, and that's 4 different pieces. Segment addition postulate says you can take it apart, put it back together, it'll be the same length. As long as you got 4 pieces connected up, they're the same length. So that's 18. This is only 2 pieces. Okay, let's do algebra. 4 pieces is the same thing as 18 centimeters. Well, 2 pieces is going to be the same as how many? God, stop. Who screwed up a problem like this before solving it? Oh, you cross multiply. I remember from class. God, first of all, we don't cross multiply in here. It only works 90% of the time. Your teachers teach you it because 90% is good enough for an A, right? Here's how you solve a problem like this. We do not say division. Think about it this way. The relationship between 4 and 2, you got that? Is the same as the relationship between what and 18. 4 and 2 relates the same way as 18 and what? Duh! Meanwhile, your teacher's having you cross multiply. The 4x equals 36. I hope I got that right, and it's 9, right? And you're pulling out your calculator. You know how dumb you look? And it's not your fault. They've taught you this is how you do math. You get out the calculator and you type it in. You wouldn't do that for 5 plus 7, or 5 plus 2. You might do it for 5 plus 7, let's be honest. This one's just as easy. It's twice as big. How do I know it's twice as big? Because division tells you the relationship. 4 is twice as big as 2. Is 18 over 9 2? Yeah, because when you divide it, you get 2. Their relationships are the same. They're the same. So if 4 gets you 18, 2 is going to get you what? 9! You know what I'm talking about. I like this kid. I like this kid. No smiling in math class. There's no happiness in here.
Matt, we'll smile.
Andrew, I'm not talking to you. I'm looking past you. I hate when that happened. I used to play drums in the band, and you're always in the back. He'd be like yelling at a trumpet player, but he wouldn't say the guy's name. He'd just yell at him. Why do you keep screwing up? And I'd be like, ah! And I realized like halfway through, like I'm like ready to go. I'm so sorry. And he's like, Ron, and I'm like, oh. I hate that. Isn't that the worst?
Yeah.
Like you're in a store and they're like waving at you. You're like, is it me or are they waving at the guy in front of me?
So you gotta do like this little.
Yeah, he's gonna go like.
Yes. My beautiful luscious hair.
That's right. Yeah. See, I'm running out. This will be the last haircut I ever need. All right. So 18, 18, and 9. How would you add them up? You wouldn't just do 18 plus 18 plus 9 in your head, would you? Because like, you know 18 plus 18? Maybe you do. 36? If I didn't, I would do 10 and 10 make 20, 8 and 8 make 16. Are we cool with 16, right? 20 and 16, 36. Okay, 36 plus 9. Maybe you know that. 45, right? You could do 36 plus 10, get 46, and then subtract 1, yeah? Right? These are useful skills, right? You want to be a wizard on a job site, that's the way to do it. Another way, 9 plus 9 plus 9 plus 9 plus 9. There's 5 9s here. 9, 9, 9, 9, 9! 9 times 5. Well, I have that one memorized. I remember getting, I got the ice cream. I got it for the 9s. I got the ice cream for the 9s in the 5th grade. I got the, did you do the ice cream thing? They had you memorize the stuff and you got ice cream? Thank God, this kid has not been traumatized. You guys have. What happened to them? You missed this beginning of the year. The teachers in like 5th grade or whatever, if they memorized their 1s, 1 times 1, 1 times 2, all that, they got a vanilla scoop of ice cream on the board, right? And if they got their 2s, then they got a chocolate on top of that. There are kids with no scoops. And then they had a real ice cream party.
Yeah, they
traumatized these kids. And what's great is you got the kid with all the scoops, and they're like, oh, I memorized all the way up to 12 times 12. You got some 12 times 13, they have no idea how to do it.
Oh, I was one of those.
Right?
Kids.
It's just 12 more, you dingus. They don't know what they're talking about. They just memorize stuff.
Yeah.
What are we doing?
I fumbled.
God, we're teaching compliance. Oh, good job. You followed the rules, and you're going to get ice cream for that. Good little soldier, right? Come on, man. Like, maybe that's a good thing. Maybe you want to be a soldier. That's fine, but like, is that what we're signing up for?
Yeah.
I don't know. Education? I don't know. You tell me. It's up to you.
I mean, you got the backpack.
It's true. My cousin's a Marine, so I get it. There's something to be said for following orders. I get that. You can work together a lot more efficiently. But in school, do it our way or else. I bet you all love that, right? Eyes on me.
No.
How many of you guys have your eyes on me right now and aren't thinking what I'm saying? Exactly? Right? Come on. And then we say, okay, they're learning. All right. 9 times 5 is 45. Maybe I didn't get the ice cream for that, right? So I don't know what 9 times 5 is. You know what 10 times 5 is? 50. 9 times 5 is one less group. You were laughing at the 12 times 12, couldn't figure out 12 times 13. 10 times 5 is 50. 9 times 5 has to be 45. One less group of 5. Now imagine if we taught you how to think like that. We wouldn't have to spend 2 years memorizing this crap and traumatizing. Because you could figure it out. I know 10 times 5. I can figure out 9 times 5. I know 10 times 50. I can figure out 10 times 49. One less group of 5. When we teach you to memorize stuff, as soon as it's something you haven't memorized, you're screwed. Anyway, 9, 18, and 18. 45. Now the real question. That was just review from yesterday. Kids, if you could do me a favor, I'm not going to try and police you because 1, I can't, and 2, I don't want to. But if you could make sure that you watch the video from the day before, either live or at some other time, then I can really get to the meat. We can start moving ahead. I'm going to start doing that. You don't need to feel bad. I'm going to start doing that because, you know, that's just how it's going to be. I got things to do, people see. Next problem. Oh, yeah, we got a new camera. Got a board camera. It's a little twitchy. I got to get a new one. That's the free one the school gave me.
That's again.
Can go up there and talk. Oh, it's not even twitching now. Oh, well. There you go. That's how it works, right? So anyway, we got this weird shape. We have all 3 shapes, flavors of shapes. We've got squares, rectangles, and that guy. Now remember, this is just a drawing. I have to play this.
Take it easy, it's just a drawing.
Okay, so it's not drawn to scale. And if we want to measure this, we can only measure it with the object itself. We can't bring in a ruler, okay? So they want to know, what's the perimeter of this shape given this? And you guys are like, oh, boring, right? But now, where are your gods? This whole thing in red is 13 centimeters. How do you solve a problem like Maria? Yesterday, Logan was in class, and he said, look, I can extend this down That might help, because now it's a shape I know about. Whenever you get stumped with a weird problem, try to think of one that's similar and see if you can learn something from that. And if you do, apply it to the hard problem. This happens all the time in science and math. Problem I struggle with for hundreds of years. One guy comes along and is, isn't that just the same as this? And they go, no, but it's really close. Oh, that's not hard. Okay. So Logan says, look, I understand rectangles. And we know we're allowed to measure using the object. So check this out, check this out, check this out. When we measure stuff, we put something up against it, right? And if it's the same, then we know it's the same. Like, for instance, these two pens, you don't know how big they are, but if I put them up together, you know they're the same. How do I know that this is the same as this? Let's put letters so we know what we're talking about. How do I know AB is the same as... How do I know AB is the same as EC? How do I know they're the same length? You can line them up, yeah. See how this is directly above it? So it's kind of like when I take the pens and I do this. Look, see, they're the same length. I don't need to know that they're 5 inches. I just need to know they're the same, right? So this is the same as this whole thing. I'm going to do that so you can tell. I'm using tick marks. Okay? They're the same. This is the same as that. Do I know that this is the same as this? That AB is the same thing as BC? Can I line those up? No, I can't, right? Could they be the same? Oh, yeah, sure, man. Right? X plus Y equals 10. They can both be 5, right? They have to be? Well, they could be 8 and 2. I know this and this adds up to 13. Do I know that that means that's 6.5 and that's 6.5? No. It could be 10 and 3. I don't know. Take it easy. It's just a drawing. But I do know that this is going to be the same length as what? BC has to be the same length as... Oh, she's getting out the calculator. Crunching those numbers. Divide by root. What do you say? Has to be, right? Okay. So if that's the same as that, and that's the same as that, I don't know how long this is, but I know that this and this adds up to 13. So in other words, AB plus BC, that's the L, right? That adds up to 13. But I also know that AB is the same as EC, right? So instead of writing AB, I'm just going to write EC. And I know BC is the same as AE. So this and this is the same as that and that. So I wrote that. We cool with that? So if this is 13, doesn't that mean this is 13? Now we've solved an easier problem. What's the rectangle, right? But I want this. And this is where I'm leaving you. You need to write about this in your portfolios. Write about the first two that are on here. Hopefully you can explain how to solve those, right? I see the L, I see the relationships, right? The third one, you might not get it. It's kind of a hard one, right? But I want you to take a crack at it and give me your reasoning behind it, okay? And then we'll talk back and forth through the comments. We're not done yet, but I just want to say, oh, I guess we are. Get out of here!
They're leaving. Have a good day, Mr. Matt.
Later. Gage, you good on the portfolio and how to, like, use it? Yeah? Okay, cool. Give this a shot, man. If you need to meet with me, I'm available after school. Eads, I don't want to see half of your face.
I'll come in after school since they're trying to get everything figured out.
Okay, if you want to.
All right.
I'll be here. Take it easy, bud. That's how you do it.